Hello everyone, I hope you all are doing well. So this is my first video after um, my university has started, and actually today was my last exam of the semester, so today Friday. And today we're doing 9701, actually 9702, May June 2017, paper 1-3 of physics. So I don't usually do physics past papers, but I was requested to do this paper, so let's do it, okay? Question number 1. What is the best estimate of the kinetic energy of a family car traveling at 50 kilometers per hour? So they're talking about kinetic energy, and the formula for that is kinetic energy equals to half mv square, right? And it's kind of hard to estimate kinetic energy, I suppose, because we don't really think in terms of energy, I suppose, really. But then we can much more easily estimate a mass, right? Like a car might have a mass in the magnitude of tons. So the magnitude of tons in kilograms would be like 10 to the power of 3 kilograms, right? So I'm assuming the mass to be in that magnitude. And if I assume that, then I can find the kinetic energy to be half into 10 to the power of 3 kilograms. So I'm just doing it in SI units because this is joules, right? So I'm going to keep everything in SI units. The volume is, sorry, the velocity is 50 kilometers per hour. So that's 50 kilometers. Let me convert that to meters. So 1 kilometer has 1,000 meters. And then per hour, right? Per hour, this is per hour. So I'm going to convert that from hours to seconds. So 1 hour has 3,600 seconds, or you could say 16 to 60 seconds. And then because in the formula this is squared, so I'm just going to square this. Yeah. And I'm just going to calculate this out. So let's see, 0.5 into 1,000 into 50 into 1,000, and then divided by 3,600. Oh, I forgot to square, sorry. Hopefully you guys are better at using calculators than me. I just got a new calculator for university. So okay, the answer I got is 9.64506 into 10 to the power of 4 joules, which I can, because it's 9.6, almost 10, so I can say this is approximately 10 to the power of 5 joules, right? And if I look at these numbers, right, so I have 10 to the power of 3, 10 to the power of 5, 10 to the power of 7, 10 to the power of 9. Then the one that's closest to the answer I got is 10 to the power of 5. It's B, right? So that is why I'm going to say the answer is B. And now well, I suppose you could do this in another way, wherein basically instead of assuming a mass, you rearrange the formula. So you get 2, like I'm going to put the formula in terms of mass. Okay, so M equals to 2 times the kinetic energy divided by V square. And so you calculate this quantity for all the options. So basically you're kind of solving the question in reverse. So for example, M is equals to 2 into the first option, so 1.5 into 10 to the power of 3 divided by the velocity, so 50, but then in SI units, so into 10 to the power of 3 into 1 over 3,600, okay, and square that, obviously. So then that gives me the answer as 1 over 3,600 squared, yeah. So that gives me the answer as 15.552 kilograms, okay? So for this one, I got 15.552 kilograms. Now if I do the same thing for B, so instead of 1.5 into 10 to the power of 3, I just write 1.5 into 10 to the power of 5, so I get 1555.2 kilograms. And then for C, if I do it, then I get the answer as wait a second, let me just fix that. Yeah, I'm having a lot of calculator issues today. Anyways, the answer I get, well, I mean, it's just going to be 2 orders of magnitude higher. I suppose that's kind of the way to think of it. Anyways, it's 155,520 kilograms. And then if I do it with 10 to the power of 9, then that's just going to be, well, 1555200 kilograms. I suppose you could write it in SI notation if you want. Anyways, that's too unreasonable. That is also too unreasonable. And now if I compare B and C, well, I mean, you kind of just have to, for estimation, you have to just kind of have a feel for it, like, how much an object weighs, what's the length of something, what's the speed of something. You just kind of have to figure it out from, well, nature, I suppose, like, yeah. I think textbooks should also have some common values of these things. But anyways, the answer will be, like, again, 10 to the power of 3. The magnitude should be 10 to the power of 3. So again, 1000. So then B is going to be the answer, okay? And anyways, I'm going to just erase this and let's go to question number 2. The diagram shows two vectors x and y. The vectors are perpendicular to one another. Okay, so they're perpendicular. Now, what is the magnitude and direction of vector x minus y? So if it's x minus y, well, x is going in this direction, so we can just keep it like that, but minus y. So minus y means we have to reverse this arrow, right? So I'm just going to reverse that arrow. And so this is minus y, okay? And the magnitude of this is 6.0 newtons. Still, obviously, it's just the direction is reversed. And then if we take this is going to be the vector that we have. So from the tail, oh no, my pen is not going up here. From the tail to the head. Okay, so it's going like this. From x to y. Okay. And I'm just going to draw it like that. So then what is the magnitude and direction of vector x minus y? So this is a right angle, and therefore if you want to find the magnitude, we can just use the Pythagorean theorem. So then we're going to have the magnitude of x minus y as, I'm just putting modulus signs, but root of, I suppose that's not mathematically correct. Anyways, the magnitude is going to be root of 8.0 square, is it? Anyways, root of 8.0 square plus 6.0 square. I suppose it's more important to get the answer. 8.0 square plus 6.0 square, so that is going to be 10.0 newtons. So we can cancel out options C and D for that reason. Now, they're saying at an angle of 37 degrees downwards or 53 degrees downwards, and then they're using downwards, upwards, downwards, upwards. Well, and from the direction of x, right? So if I go from x to my vector x minus y, I have to go upwards. So because I have to go upwards, I can cancel out options, let's say downwards, so I can cancel out option A and I can cancel out option C. Okay, so I basically already have the answer as B, but if you want to be sure, you can obviously calculate out the vector, the angle as well. So this is the angle I want. I'm going to call it angle theta, and then according to sine, cosine, those things, we can see that this is going to be opposite over adjacent if I use the vectors x and minus y. So it's going to be opposite over adjacent means tan. So tan theta is equals to opposite, which is going to be 6.0 newtons, because that's the value of the minus y vector, and then divided by the x1, which is adjacent, so 8.0 newtons, right? And so my theta is going to be tan inverse of 6 over 8, so that is going to be 36.86989, so on. So it's approximately 37 degrees to two significant figures, and so our answer would either be A or B, but because we already figured out that the direction is upwards, so it is going to be B then, right? So 10.0 newtons at an angle of 37 degrees upwards from the direction of x. Okay, so that's the answer. Now let's go to the next question. So the question is, which expression using SI base units is equivalent to the volt, right? Well, we know that voltage is defined as work done, or you could say, I suppose, energy um per unit charge, right? Or you could also say energy per unit charge. And if then you have EMF and PD. So the EMF would be the work done per unit charge in driving the charge around a complete circuit, whereas the potential difference would be the work done per unit charge to move the charge from a point A to a point B across the circuit or across a component. So anyways, we have work done per unit charge as the definition of voltage, and then we know that work done is also equal to force multiplied by distance, or actually displacement technically, right? Because force is a vector, displacement is a vector, and then when you take the cross product of those, sorry, the dot product. Yeah, sorry. I should know this, man. I just did vectors a few weeks ago in university. Anyways, so you do the dot product of the two vectors and you get a scalar, which is work done. But anyways, you have work done as force multiplied by displacement divided by the charge, and then we know that F equals to ma as well, so we can simplify this further as ma times the displacement, and then Q, the charge, we know that charge is also equal to IT, right? Because current is the rate of flow of charge. So I equals Q over T, and then if you just cross multiply, then you get Q equals IT, right? So yeah. Anyways, the point is that this is the equation that I get, and now I know the units for all of these things, so that's why I wrote the equation. So mass, the unit is kilograms. Acceleration, the unit is kilograms, kg, kilogram. What am I even saying? I don't know where my brain is right now. Anyways, kilogram. Acceleration is meters per second squared, right? Um, Obviously, because acceleration is velocity over time, or the rate of change of velocity actually. So dv over dt, but then that is going to be, velocity is meters per second, and then time is obviously seconds, so that's going to be m s to the minus 1 into s to the minus 1, so that's going to be ms to the minus 2. So that is the thing. Anyways, never mind. I'm pretty sure that is quite obvious that acceleration has a unit of ms to the minus 2. And then displacement, this is displacement, by the way. In case you're not used to like the symbols or stuff, I'm just clarifying. Anyways, displacement is obviously going to be meters, and then current is going to be in amperes, and current is also an SI base unit, so I don't need to simplify that further. Whereas charge, obviously you have the unit of coulombs, but that is not an SI base unit, so that's why I wrote it in terms of current, because current is an SI base unit. So you have 7 SI base units, and those are kilograms, seconds, meters, amperes, and you also have moles, candela. Yeah, I mean, how many is that? 1, 2, 3, 4, 5, 6. Okay, so I have one more. Yeah, kelvins, temperature. So we have kilograms, seconds, meters, amperes, moles, kelvins, and candela. So the SI base units. So yeah, anyways, current is an amperes is an SI base unit. And then for time, we're going to have seconds. All right, so those are the units, and then I'm just going to move these to the numerator as well. So kg times m, and this becomes, because you have m times m, so that's going to become m squared. Then you have s to the minus 2 multiplied by this one goes to the numerator, so it becomes s to the minus 1. And then you have times a to the minus 1. So that's going to be kg m squared s to the minus 3 a to the minus 1. So let's see which option matches with that. So kg m squared, no, that doesn't match, that doesn't match, that doesn't match. That matches kg m squared s to the minus 3 a to the minus 1. So answer is going to be D. All right, now next question. A voltage is carefully measured with a high quality instrument and found to be 2.321 volts. Two students using two different methods conclude that the voltage is 2.33 volts and 2.344 volts respectively. Which statement is correct? Okay, so they're talking about accuracy and precision. Okay, so let me So this is my value that, the actual value from careful measurement. I mean, I don't know if it's the actual value, but like, carefully measured with a high quality instrument, so it's much more of an accurate value, I suppose. So 2.321 volts, right? And then you have the first student, um, his value or her value was 2.33. So then 2.33, I'm just going to find the difference between 2.33 volts minus 2.321 volts, all right? Like from this value with the the actual value in quotations, because I mean, it's still a measured value, but like it's much more accurate than the student's values, I suppose. So 2.33 minus 2.321, so that is going to be a difference of 0.009 volts. As for student 2's value, you have 2.344, right? So 2.344 minus 2.321, we're going to get 0.023 volts. So as you can see, because they're talking about the value of 2.33 volts, like is it less accurate, less precise than 2.344? So I'm going to compare the two values and let's see. So student 1's value was like the difference between student 1's value and the actual or perhaps the more accurate value is so the difference between those two is 0.009, whereas the difference between these two values is 0.023. So as you can see, this is a much smaller difference. So that means that student 1's value is more accurate, right? Because it's closer to the true or to the known value. Okay, so therefore if they're saying 2.33 is less accurate, that's wrong, because it's actually more accurate. Okay, and then they're saying less precise or more precise. Well, if you compare the two digits, 2.33 and 2.344, so as you can see, this one has only 2 decimal places, whereas this one has 3 decimal places. So it's definitely that 2.33 is less precise, because it is to only to 2 decimal places, where this is to 3 decimal places, so it's known to a greater, well, precision, as the name suggests. But anyways, so if we say that 2.33 volts is more accurate, yes, but then less precise as well. Okay, so we are going to, where do we have two ticks? We have two ticks at C, so C is going to be the answer. So 2.33 volts is more accurate because it's closer to the known true value, and it's less precise because it has less significant figures or less decimal places. Yeah, so that is going to be the answer. Anyways, on a planet, a vertically launched projectile takes 12.5 seconds to return to its starting position. The projectile gains a maximum height of 170 meters. The planet does not have an atmosphere. So what is the acceleration of freefall on this planet? Okay, so let me just draw a diagram. So you have a vertically launched projectile. It takes 12.5 seconds to return to its starting position. So I'm going to say that if it takes 12.5 seconds to return to its starting position, I mean, that's probably not an accurate diagram. Let me just redraw this. So it's going more like this, and then it's returning to its starting position. I mean, it's a projectile anyway, so why did I erase that? The point is that it has a start to its journey and then an end where it returns to its starting position. I mean, assume that it's this big, so it's returning to its starting position. Anyways, the total displacement is 0, basically. Anyways, so if it takes 12.75 seconds to go to and back, then that means for half of the journey it will take how much time? 12.5 divided by 2, which is going to be 6.25, I think. Yeah, it's 6.25. Obviously, 6.25 seconds. I should get better at mental math. Anyways, 6.25 seconds. So this half of the journey is taking 6.25 seconds, and this half of the journey is taking 6.25 seconds. And you have to realize that the projectile gains a maximum height of 170 meters. So this means its total displacement in one direction is 170 meters. Okay, its maximum height basically that it gains. And at maximum height, obviously, it will have a velocity of 0, because velocity is the rate of change of displacement, right? And so if you have the maximum velocity, then that means the maximum displacement, the maximum displacement means that your velocity equals to 0. Yeah, so over here you have the velocity equal to 0. And the planet does not have an atmosphere. Okay, so you don't need to consider friction effects and stuff. Okay, now air resistance. Yeah, so what is the acceleration of free fall on this planet? So we can use our Suvat equations. What are the Suvat equations? Well, we have S is equals to ut plus half at square. We have S equals vt minus half at square. We have v equals u plus at, and also v square equals u square plus 2as. And then we also have S is equals to u plus v by 2 into t. So this is the 5 or so Suvat equations. Okay, so let's see what quantities we have. Well, we have the displacement as 170, so that quantity we have. We have acceleration, but we don't have acceleration, but we need to find it. So we do need an equation that has acceleration basically. And we have the time, which I told you, like firstly they've given 12.5, but then half journey is 6.25, and that's much more useful for us over here. So we will also, because none of these equations have only S, A, and T, so we also need either of U and V. So we can take either of them really. Basically the equations we would use are one of these, S equals ut plus half at squared, or S equals vt minus half at squared. It depends. I mean, me personally, I'm going to use, for example, S equals vt minus half at squared, and for that I'm going to take this I'm going to highlight it. So I'm going to take this journey. So in this journey, because v is my final velocity, right? So in this journey, because I'm considering it till the maximum height, right? So the maximum height, I have velocity equals 0, which means I don't know the initial velocity, but the final velocity was here 0, right? So that means this term goes to 0 because my final velocity was 0. So then I get the displacement. Obviously we're going upwards. I'm going to use the sign conventions. This is positive. So my displacement is 170 meters equals to minus half a, so I don't know a actually, and then t square. So t square, because it's half the journey, so I'm again, I get 12.5 divided by 2, that's 6.25. It's going to be 6.25 square seconds squared. So then my answer is going to be basically a is equals to, I'm going to rearrange this, minus 2 into 170 meters divided by so 6.25 squared is actually 39.0625 seconds squared. And so you're going to get the answer is minus, so 2 into 170 divided by 39.0625, that gives you 8.704 meters per second squared. All right, and obviously if you look at the options, you get the answer is B basically. But then you might ask why we have a minus sign. It's because the acceleration due to free fall is always negative basically. That's kind of how it's defined, it's defined downwards, acceleration due to free fall. So yeah, it's defined in this direction. And let me also clarify one more thing, that I use this equation S equals vt minus half at squared. You could very well, as I mentioned before, use the equation S equals ut plus half at squared as well. And instead of considering the first half of the journey, you could consider the second half of the journey, which I'm highlighting in pink. So basically, in the second half of the journey, again, you will consider that because you're at the maximum height initially for the second half of the journey, like you start from maximum height, so your u equals to 0 here. So this term again just goes to 0, and then because you're going downwards here, and I considered my sign convention as the displacement is positive upwards and then downwards is negative, so I'm going to write minus 170 equals to half at squared. And then again, if you solve it, you will solve the equation and substitute the value for t as 6.25 and everything. Then you will get the answer again as minus 8.704 meters per second squared. By the way, guys, I have not done questions of AS physics for a very long time, so if I am making any mistakes or saying any wrong concepts, I would really appreciate if you wrote it down in the comments so that other people are able to get the correct information, if I say anything wrong. Okay, I would really appreciate that. Thank you. And now question number 6. I'm just going to erase this stuff. Yeah. A displacement time graph for a toy car is shown. Which graph shows the variation with time of the velocity v of the car? Okay, so again, as I mentioned before as well, velocity equals to the rate of change of displacement, right? So ds dt, basically, or you could just simplify it to st, but it's the gradient basically of this graph, right? The gradient of the displacement time graph. Okay, so which graph shows the variation with time of the velocity v of the car? Well, if I calculate it, I mean, I suppose they've already given you the values as well, so that's kind of more convenient. I'm just going to write 1 and minus 1 as well, because yeah. So each box is 1, and then this on the y-axis, and then over here on the x-axis you have each box is 2 seconds. Okay, now anyways, firstly, if I find the gradient of this portion of the graph, I'm going to have it as v equals delta s over delta t. So then that's going to be the change in y over the change in x, right? So that's going to be 2 minus 0 divided by the change in x over here for this portion of the graph. Okay, so 2 minus 0 again. So that's going to be 2 over 2, which equals to 1 meter per second. So if I see my graph options, I have 1 meter per second here, positive, and this one is starting with 2, so that's wrong immediately. This one has minus 1 for some reason, but that's wrong because obviously my displacement, you can see the gradient is positive here because it's an upward slope. So upward slope implies positive gradient, so then C has to be wrong for that reason. D, on the other hand, it does have a slope of 1, so D is still a possible option. So my possible options till now are A and D. Okay, now let's consider the second portion of the graph, which is this portion from 2 to 4 seconds of the displacement time graph. So over here, if I calculate the gradient, well, obviously the gradient is 0. You can see that because it's a straight line like this. So but if you want to see it in equation, well, I mean, you just have 2 minus 2 change in y over the change in x, which is 4 minus 2. So you have 0 over 2, which is obviously going to be 0. Yeah, so the velocity is 0 meter per second, which means it's basically, yeah, the velocity is 0. So let's see which graph has that. Yeah, this is just showing an abrupt change, so that doesn't really affect anything, but I mean, it's just how you draw a graph. I suppose you could also not draw it, but anyways, the point here is that 2 to 4 is shown as 0 here and 0 here, so A and D are both still contenders. As for the next portion of the graph, which is from 4 to 6, from 4 to 6, I calculate the change in y over the change in x. The change in y is, change in y means the final y minus the initial y over the change in x. Change in x is much more easy, I suppose, because 6 minus 4, right? But then if you calculate the change in y final, so y final is minus 2. So minus 2, and then the y initial is actually, again, 2. So minus 2 minus the y initial, which is 2, divided by 6 minus 4 is 2. So you get v equals minus 4 divided by 2. So v equals to minus 2 meters per second. Again, we're getting negative values because this is velocity. Velocity is a vector quantity which has a magnitude and a direction, right? Because we're considering a displacement time graph, but then speed will only have a magnitude because it's a scalar quantity. Okay, so that's why we're getting, it's very possible to get negative values for velocity, so this is very possible for our answer. So we get minus 2 meters per second for this region. So basically what this means is that this is a positive slope and this is a negative slope. So we had positive velocity and negative velocity, but then this velocity is actually double the magnitude as well of this velocity. So this slope is double this first slope. Okay, anyways, so we got minus 2. So let's see A. So A shows this region as minus 2, but D shows this region as plus 2. So that means that D must be wrong. Okay, so then A is the answer basically. And now if you look at from 6 to 10, 6 to 10, again we have a constant velocity because it's just the displacement is minus 2, which is constant. So then the velocity is going to be constant because the gradient here is 0, right? So velocity is 0, I mean, because the displacement is constant. Velocity equals 0 if displacement is constant. Yeah, so and this is shown in this graph correctly as well as in D, but like D was wrong for this reason that the region from 4 to 6 is shown as plus 2, whereas it should be minus 2. Okay, so the answer is going to be A. And yeah, let's go to the next question now. Question number 7. A driver stops his car in time t by gradually increasing the total braking force on the car. The graph shows the resultant force on the car. All right. Now the question is, which graph shows how the speed of the car will vary during this time? Okay, so well, we basically have to compare the gradients of the graphs, so speed time graphs. We know that acceleration is the rate of change of velocity. Right? I mean, we have speed here, but like the general idea is this, right? And obviously, I suppose if you take the modulus of acceleration, that's going to be the change in speed. Speed denoted as v as well. Anyways, the point is that this graph has something to do with acceleration, and since we have a force time graph, we know F is equals to ma, right? So I could basically that means that if the mass is constant, which obviously for a car you would assume it to be constant, I suppose. Um, but then yeah, we assume that to be constant, so then that means that F is directly proportional to A. So that means that if this is a force time graph, you can also think of it basically as an acceleration time graph. But then you have to realize that the driver is gradually increasing the total braking force in the car, right? So what that means is that if he's increasing the total braking force, which is basically kind of like a opposing force or a frictional force, like it's stopping the car, right, rather than speeding it up, obviously. So that means that he's basically um decelerating, right? So um so if he's decelerating, and again you see that from the force time graph that the force is increasing, but then actually this quantity is like deceleration. So then that means that the gradient is basically increasing of that. So then sort of like the negative gradient in the velocity time graph is increasing. But anyways, let's look at the graph rather than talking so much. So over here you have the speed time graph. You can see that the gradient is constant in b, which is not true, because over here you can see the force is increasing with time, right? The braking force is increasing with time, which means the deceleration is increasing with time. So that means that you're not supposed to have a constant gradient graph over here. Your deceleration is the gradient, and it should not be like this, right? Acceleration technically, because I suppose it's speed, so you can consider it as acceleration. But yeah, and if you look at C, we have like an inflection point, which doesn't again really make sense over here, because you can see it's just increasing and not really doing anything else. So if it's increasing, you would expect a kind of more um beautiful trend than an inflection point, right? There should be no point like that really. um so then we consider graphs A and D, and actually you have to think of it a bit like this, that A implies that he is actually decreasing um the force with time, but actually it's saying that he's increasing the total braking force in the car. But A would imply that he's decreasing the total braking force in the car, because you can see that the gradient with time is approaching zero, or like becoming smaller. So gradient is becoming smaller with time here, right, in A, which is the opposite to the trend we want. So this implies that he's decreasing the total braking force of that car with time. But actually, if you look at D on the other hand, because we already cancelled out A, B, and C, you can probably tell the answer is D. But then if you look at it, then you start out with the gradient like zero, means the acceleration is around zero, and then you slowly increase the acceleration. So if you obviously he's increasing the total braking force in the car, which means the acceleration is increasing. I mean, I'm saying acceleration because it's a speed time graph, but then you have to realize it because he's actually decelerating. Yeah, because his speed is decreasing. The car's speed is decreasing. I mean, eventually it's stopping, I mean, of course. So then our answer is going to be D, where the gradient is increasing with time, as because the total braking force in the car is increasing with time, so the gradient is increasing with time, and it cannot be constant. It cannot have like this weird inflection point thing, and it's not decreasing with time either, so it's going to be D. All right, G. So that is the answer. Now the next question. The graph shows the variation of a quantity y with a quantity x for a body that is falling in air at constant terminal velocity in a uniform gravitational field. What quantities could x and y represent? So it's kind of showing proportionality, I suppose, because this is 0, 0. So now, what quantities could x and y represent? So it is constant terminal velocity actually, which means it's the maximum velocity. Again, we know that acceleration equals dv dt. So which is the rate of change of velocity. And so if we have constant terminal velocity, that means that our velocity is maximum, right? And it's constant. So then that means that acceleration is basically 0. Yeah. So your velocity is remaining the same. So now let's look at the options. First, we have the x being a resistance and y being acceleration. That is not true or impossible, because acceleration, as I already mentioned, is 0, and this is for a body that is falling in air at constant terminal velocity, right? And at terminal velocity, your acceleration is 0. So that means we cannot have acceleration supposedly increasing like this, right? You cannot have it like that. So you cannot have this as the correct answer. As you look for as for option B, you have loss you have loss of height on the x-axis and gain in kinetic energy on the y-axis. Again, this is wrong, because gain in kinetic energy implies that your speed is increasing, because yeah, again, gain in kinetic energy would imply that your speed is increasing or the velocity is increasing, but then again we have constant terminal velocity, which means your velocity is constant. It's the maximum value. So B is also wrong. If you look at option C, it says that on the x-axis we have loss of potential energy, and on the y-axis we have work done against air resistance. That is a probable answer, because obviously, because we're falling. I mean, we're not falling. I mean, the body is falling. I hope it's not a human being, but anyways, falling, and that means you have obviously loss of potential energy, and then by the law of conservation of energy, you if your potential energy is decreasing, it should be converting into something else, right? Like, how is it just decreasing and nothing else is happening? So if we have the answer to that question, that oh, the energy is actually like work done against air resistance is happening, so that's what is the energy balance, then that actually makes a lot of sense, right? Because obviously, because it's terminal velocity, we don't have any kinetic energy change. But then if you have loss of potential energy but also work done against air resistance, then that does help us show that energy is still conserved, which is obviously a rule of physics, right? So then that implies that C is probably the answer, but just to check, we can also look at option D. In D, we have x-axis as time and y-axis as velocity. Again, that is not very possible in this situation, in this scenario that we have considered, because again we have constant velocity, right? As I've mentioned quite a few times. I suppose I repeat myself a lot, but anyways, we can't have that because again it's constant velocity. So D is going to be wrong. And now let's go to the next question. A ball of mass 2.0 kilograms travels horizontally with a speed of 4.0 meters per second. So this ball has a mass of 2.0 kilograms and it is traveling horizontally with a speed of 4.0 meters per second. Actually, let me take this as my initial velocity, like our speed, but like initial velocity, 4.0 meters per second. So I'm going to denote that as u, the variable u, and then the ball collides with the wall and rebounds in the opposite direction with a speed of 2.8 meters per second, which I'm going to denote as v as my final velocity. Okay, 2.8 meters per second. And the time of collision is 150 milliseconds. So t is equals to 150 milliseconds, or actually let me say delta t, so the change in time, so it's the time of collision, right? So the time it spent interacting with the wall. So what is the average force exerted on the wall? So we know the definition of force. Force is defined as the rate of change of momentum, as dp over dt, or delta p over delta t, right? So then we know that momentum is defined, so momentum is defined as mass times the velocity. So then, because we have the rate of change of momentum, that means well, that means we're going to take delta p. So delta p is going to be the mass times the change in velocity. So that is going to be mass times the final velocity minus the initial velocity, which, I've denoted these two here, that's why. And so one thing we should do here as well, and I've already written as that delta t is 150 milliseconds. So then F is going to be equal to m v minus u over delta t, which is actually 150 milliseconds. So 150 into 10 to the power of minus 3 seconds. Okay, and then my F is actually going to be equal to, so my mass was 2.0 kilograms. So 2.0 kilograms multiplied by velocity, final velocity. So final velocity, okay, so let me just do a sign convention, because again, this is not speed in the formula, it's velocity, right? So let me, my sign convention for this, and you can have, the opposite sign convention is fine, because again, it's the more the magnitude that matters, and like in questions like these at least. So anyways, this direction, I'm going to take the right as positive and the left as negative. Okay, so therefore, if I have the final velocity is going to the left, so it's negative, so it's going to be minus 2.8. As for my initial velocity is going to the right, so it's 4.0, so I'm going to take that as just positive. So plus 4.0, which is simply, you can also write it as 4.0, and the units are meters per second. Yeah, the habit I've gotten into after being in university, because I'm doing engineering actually, so then, there's a lot of dimensional analysis, so I tend to write the units in my formulas now, but in my calculations. So yeah, anyways, if you calculate this out, so 2.0 into minus 2.8 minus 4.0, that is going to be in the numerator minus 13.6, and then divided by 115 to 10 to the power of minus 3, that's going to be 0.15, and then I'm just going to combine the units, so kg ms to the minus 1 multiplied by, this goes to the numerator, so it becomes h to the minus 1. So that's going to be minus 13.6 divided by 0.15, so that's going to be minus 90.6 kg ms to the minus 2, which is approximately minus 91 kg ms to the minus 2. So the answer is around, well, I mean, if I look at the options choices, then D is the closest answer. Now, the thing here is you also have to realize that the question asked for the average force, and yeah, it's very, very true that this is the average force that we have calculated, because obviously you can't expect the force to be constant during this entire collision period of 150 milliseconds. You can't expect the force to be constant, firstly, and secondly, you can see that the initial velocity was 4 meters per second to the right, and then the final velocity was 2.8 meters per second to the left. So you can see that the velocity, or the magnitude of velocity of the speed, has decreased, which means obviously that you lost energy, which means that if there was loss of energy, then obviously, that you didn't have constant force throughout that duration of the collision. So this is the average force rather than, it is the average force that you have calculated using this equation. So that is something to realize as well. And also, another thing to realize is that I have actually not calculated the force of the ball on the wall, because the force of the ball on the wall will be in this direction, right? Let me use another color of pen perhaps, but you have to, like, so basically the force of the ball on the wall would be in this direction obviously, but the force, because they're asking for the force on the wall, so that's going to be in that direction. So force on the wall, force, oh actually I did calculate that, right? Never mind. So I did it because yeah, I didn't read the question correctly. Force of the ball on the wall, so that is in this direction. And I got the, actually no, never mind, I don't know what I'm saying at this point, but the more point, you don't need to complicate things so much actually, because you already got the answer, but then I just want to clarify something. So the force is minus 91, right? So that means, because I defined this direction, the right to the positive and the left as negative, that means I got the force in this direction, which is minus 91 kg ms to the minus 2, right? And kg ms to the minus 2 is obviously a Newton if you use the if you're writing in SI base units. So then that means I calculated actually the force of the wall on the ball, right? but then actually the force of the ball on the wall is equal to, but opposite in equal in magnitude but opposite in direction to the force of the wall on the ball, right? So so the one that I had to calculate was force of the ball on the wall, which would just be, instead of minus 91 kilogram per meter, instead of minus 91 newtons, it would be plus 91 newtons because it's going in that direction. So simply, because we got a negative answer because I calculated that force, but then the other direction will obviously be plus 91, right? So that's just something, that's just Newton's third law, that for every action there is an equal but opposite reaction. So that is basically the point, that the force of the ball on the wall is equal to the force of the wall on the ball, but then just opposite in direction, right? So yeah, so that's I don't know why I gave such a convoluted explanation, but I hope you understood my point. Anyways, the answer is 91, so that's nice. So now let's go to the next question, question number 10. Let me erase this stuff. An ice hockey puck of mass 150 grams moves with an initial speed of 2.0 meters per second along the surface of an ice rink. The puck slides a distance of 30 meters in a straight line before stopping. What is the average frictional force on the puck? All right, so let's make a diagram firstly. So I have an ice hockey puck, and its mass is 150 grams. So the weight basically then equals to 150 into 10 to the power of minus 3 kilograms times the gravitational force constant, but never mind. I'm just going to write for now that the mass equals to 150 grams, okay? With an initial speed of 2.0 meters per second along the surface of an ice rink, I'm going to assume that it moves to the right. And again, I'm going to assume that this direction is positive and the left is negative. That's just my sign convention. If you wanted to take the opposite thing, it's completely fine. If you wanted to consider that your ice rink is vertical or something, that is also fine. But it's just get the correct answer, I suppose. And yeah, nevertheless, so my initial speed is 2.0 meters per second. Yeah, and then the puck slides a distance of 30 meters. I feel like this is going to be a so bad question. The puck slides a distance of 30 meters. So imagine that my displacement then is 30 meters to the right. All right, let me just make this a bit more neat. So S is equals to 30 meters, all right. And I'm assuming that it stops here, that's 30 meters. Assuming, okay. Before stopping, so over here my V, the final velocity equals to 0 meters per second, okay. Now what is the average frictional force acting on the puck? So again, I really do feel it's a SUVAT question, or it can be solved using SUVAT. So we have the displacement, we have the initial velocity, we have the final velocity, and we need to find the average frictional force. Now we can just use the formula that resultant force equals mass times acceleration. So F equals ma, and we know that assuming that the mass of the hockey puck is constant, which it probably should be unless friction is also causing some particles of the hockey puck to get lost or something, I don't know. But then in general, I mean, that would be negligible. So then you can assume that the mass is constant. And so your force is directly proportional to acceleration. So basically, if I find acceleration, I can use that to find my force later, because I have the mass anyways. So then I have the quantities S, U, V, A. I don't have the time, so just ignore that. But then you have S, U, V, A. So the SUVAT equation that relates those is V square is equals to U square plus 2as. Now, because I want to find the acceleration, I can rearrange this to v square minus u square over 2s is equals to a. All right, and then I just substitute in the values. So a equals to my final velocity is 0 square minus my initial velocity, which is going to be 2.0 square, and that is going to be m square s to the minus 2, because ms to the minus 1 is the unit, and because you're squaring the velocity, so it's going to be ms to the minus 1 square, so that's going to be m square s to the minus 2. And then divide that by 2 multiplied by the displacement. So displacement is 30 meters, and already you can see that this cancels, so I get the unit as m to the minus 2, which is correct because that's the unit of acceleration. Yeah, so now we're going to just, let me find the answer to this. So I get minus 1 over 15, which is minus 0.06 recurring meters per second squared. Now, let me just erase this so I have space to write. Now we know that F is equals to ma. This is the resultant force, so then we're just going to substitute the values into this. So 150 grams, so I want to convert that to kilograms. So it's going to be 1 kilogram is 1,000 grams, right? So I'm going to divide by 1,000, and then I'm going to multiply this by my acceleration, which is minus 0.06 recurring. So minus 0.06 recurring, or minus 1 over 15. So then I'm going to get, right, ms to the minus 2. Yeah, so then, and then, yeah, I get the units as kg ms to the minus 2, which is the unit for force in SI base units, or you could say Newton. So then if I do this in my calculator, I get minus 0.010 newtons, all right, which is option A. And then now we have to see why we have a negative sign, really. The reason for that is because this is frictional force, right? So I assign my left as negative, so this means that this force is actually in this direction, so minus 0.010 newtons, and it's a frictional force, so it's obviously opposing the motion, so motion is to the right, and so friction is to the left, right? Frictional force is to the left, and that's why I get a negative value for that. And so yeah, the answer is A. And obviously, again, here your velocity is changing over this time interval, right? So you would assume, like, I'm calculating the average frictional force, but in reality, because they again mentioned the word average frictional force because we're making that assumption, but then the reality is, like, obviously, of course, the frictional force is not constant in the duration. Yeah. Anyways, that's the average frictional force. For that reason, we calculate using the Stubat equation, obviously. And now we have question number 11. A uniform beam of mass 1.4 kilograms. So even they've drawn in the diagram center of beam of mass 1.4 kilograms, so they're assuming the weight is more concentrated at the center, and then is pivoted at P, or concentrated at the center, is pivoted at P as shown. The beam has a length of 0.60 meters and P is 0.20 meters from one end. Loads of 3.0 kilograms and 6.0 kilograms are suspended 0.35 meters and 0.15 meters from the pivot as shown. So what is the torque that must be applied to the beam in order to maintain it in equilibrium? So the question says what's the torque that must be applied, which implies, I suppose, that the beam is, on its own, it's not in equilibrium. So the clockwise moment is not equal to the anti-clockwise moment, which is why we need to apply an additional torque. And so, yeah, we need to apply an additional torque so that the beam is in equilibrium. So I suppose what we need to do in this question is find what's the clockwise moment, and then find what's the anti-clockwise moment, then find what's the difference in magnitude between them to determine how much torque we need, right, to apply. And let us see. So we know that moment is equals to the force applied times the perpendicular distance. That's my very beautiful perpendicular symbol, but, like, yeah, just perhaps you can be a bit more neat than me. The exam I did today, I did not write very neatly, unfortunately. Anyways, clockwise moment. So the sign convention I'm using is that anti-clockwise moment is going to be positive, and that's just because that's what my physics teacher always said. Like, nature shows anti-clockwise moments a lot, so that's why I'm assuming that to be positive and clockwise moment to be negative. Okay, so then anti-clockwise moment is going to be equal to FD, and then we're going to take the moments about this. So there's going to be just M AD, I suppose, because F equals MA. So then I have this. So the moment of 3.0 kilograms about P is going to be anti-clockwise. The moment of the center of the beam of mass, center of the beam about P is again going to be anti-clockwise, because obviously a clock goes like this, right? 1, 2, 3, 4, 5, 12. 1, 2, 3, 4, 5. Yeah. So then clockwise is going to be only the moment of 6.0 kilograms about P. All right. So in my clockwise moment, sorry, I was doing anti-clockwise. So let me do anti-clockwise first. So that's going to be minus, because that's the sign convention I use. And then the first one, I have two moments, right? So firstly 3.0 kilograms, so that's going to be 3.0 into not mean use a circular bracket, 3.0 into kilograms, sorry. The acceleration, sorry, 9.81, isn't it? Let me check if the data booklet uses that value, because I think it's different for math and like yeah, 9.81. Okay, I'm going to use that value then. So 9.81 ms to the minus 2 into the distance. So the distance from 3.0 kilograms to the pivot is 0.35, right? So 0.35 meters. And then another minus for the other moment. That is, let me just erase this and just consider one at a time. Perhaps that's more less messy that way. So this is another one that I'm considering. So it's going to be 1.4, right? So 1.4 kilograms into 9.81 ms to the minus 2 into, so it's the difference between so basically let me just consider that the whole total length of the beam was 0.60. That means half of the length of the beam is going to be 0.30, right, meters. And so because this from the distance from the end of the beam to P is 0.40, and the distance of half the beam is 0.30. So I need to find this distance. Should I like color it or something? I don't know. For this distance, so that's going to be 0.40 minus 0.30. So that's going to be 0.10 meters. Okay. So now let's just do this calculation. So minus 3.0 into 9.81 into 0.35 minus 1.4 into 9.81 into 0.10. So you get the answer as minus 11.6739 kg m square s to the minus 2, which is basically minus, again, kg m square s to the minus 2 is the same as kg ms to the minus 2 into m, right? So kg ms to the minus 2 is the unit for Newton, so Newton meters. So this is basically the same as minus 11.6739 Newton meters, which is actually the unit for moments and torques that's commonly written. So I'm just going to write Newton meters. Okay. And so instead of kg m square s to the minus 2, here I'm going to just write Newton meters to make my calculations a bit less messy seeming on this screen. Okay. Anyways, that's my anti-clockwise moment. As for my clockwise moment, that is going to be, let me just actually draw the arrows again, but now because now I've already considered the left side of the diagram, so now I'm going to consider the right side. So there I have 6.0 kilograms, right? So 6.0 kilograms, that's my clockwise moment 2p. So then, oh wait a second, never mind. For a second I was like, should I have considered 4.40, but no, this is starting from here. Yeah. Anyways, so the distance, so firstly that's going to be MAD, right? So then this is going to be plus. Did I take the opposite sign convention? Oh well, I took the opposite sign convention and I talked so much about anti-clockwise moments being, anyways, never mind. This is negative now, and this is positive, okay, according to what I did here, because I put a minus sign here, so let me just consider it as minus now. It does not really matter which direction you consider it as negative and which direction you consider it as positive, as long as you have a convention. So before I had stated that the convention to be positive as this and negative as this, which is what I would have preferred, but then For some reason, I did the opposite thing, and I don't know why, what I was thinking in my brain. But anyways, I did the opposite thing, so so it's fine. It's fine. It's totally fine. So plus, and then this is 6.0 kilograms. This time I'm not writing units just to make my calculations fit into the space. Into 9.81, and then multiplied by this distance from the mass to P, so that's going to be 0.15. All right. So that is going to give me 8 plus 8.829 Newton meters. All right, so plus 8.829 Newton meters. So obviously, as you can see, as I already mentioned, that clockwise moment is not equal to anti-clockwise moment. I would have preferred to take this as positive and this is negative, but anyways, it's fine. And now what we have to do is we have to find the torque. So torque is going to be the difference in the magnitudes of the moments. So the modulus of negative 11 point, or never mind the modulus, but basically my point is that the torque is going to be the magnitude of this. So I'm not going to consider the sign. So it's just going to be 11.6739. So the difference in the values, basically just the difference. And then minus 8.829. And so my torque is going to be the difference in the magnitude. So that's going to be 11.6739 minus 8.829, which is going to be 2.8449. Although, you know, the point actually is that even if you had considered the signs, you see that the anti-clockwise moment is much larger than not much larger, but larger than the clockwise moment. So that means that the additional torque that I must have is actually in the clockwise direction, because I have to make it like 11.6739 is equals to 8.829, but then plus 8.829, but then you also need an additional something, and obviously you have to multiply this side by minus to make it actually equal to that side. If you hear what I'm trying to say, because I know that I talk a lot about weird stuff, but then this is the actual equation that I'm supposed to, if you want to write it down, because I understand that it's kind of weird that I just randomly remove the minus sign from here. So if you want to consider it actually, then it's like this. So minus 11.6739 is equals to minus 8.829 plus x. So that's the actual equation I would have. And then you make it, multiply both sides by minus 1, so you get 11.6739 is equals to 8.829 plus x. And so the additional torque you need, x is by the way the torque, is going to be 11.6739 minus 8.829. That's going to be plus, where here the sign is important, whereas in that calculation I was just considering the modulus, so just the magnitudes. So here you get plus 2.8449 Newton meters, which means that your additional torque is a clockwise moment. So your additional torque is actually in this direction, is what this answer is indicating, because this is a plus sign. All right. But even if you don't do that, it's fine, because the answers usually I feel like in AS physics they don't tend to really, usually, I mean, obviously it's important to consider the directions, but then they usually just tell you what's the magnitude of this answer, what's the magnitude of that answer. But anyways, the point is that the answer is going to be D, 2.8449. That's approximately 2.8, correct, to two significant figures. So that's the answer, and this torque is a clockwise moment. This torque is clockwise. All right, that you need to apply. And yeah, let's go to the next question now. Okay, let me just erase things. Okay, let's look at this question. An air bubble is rising through the liquid at a constant speed. The forces on it are the upthrust U, the viscous drag D, and its weight W. Which diagram shows the directions and relative sizes of the forces? Yeah. So viscous drag D, that should be in the direction opposite to the motion. The motion is upwards, right? Rising through a liquid at constant speed, rising, so upwards. And the drag here in D is actually upwards, which is wrong, because drag must be opposing the motion, so it must be downwards, downwards, downwards. So D is wrong, okay, from the get-go. Then we have to consider the relative sizes of forces. Now again, it's at constant speed, which implies that the total sum of the forces on it is 0, the resulting force on it is 0. The upward force is equal to the downward forces, basically. And we can see that that is not really the case for B. Yeah, these forces do not add up to the upthrust, so that means that B is wrong as well. As for C versus A, The problem lies here because it's an air bubble. An air bubble is a really, really tiny thing, and it's an air bubble, right? So it would really have a very negligible weight for that reason. And it's filled with air as well, and it's an air bubble. It's very small, and so you can't really have, especially you can't really have the weight to be more than the drag force. But then the reality is that it's really small weight, so we can cancel out C for that reason. And so A is going to be the correct answer, because I mean A and C, they both showed that the upthrust equals to W plus D, but then W has to be much smaller than D and U. So that's why we have to say that A is the correct answer. Okay. Next question. The diagram represents a sphere underwater. P, Q, R, and S are forces acting on the sphere due to the pressure of the water. Each force acts perpendicularly to the sphere's surface. Okay, that's nice. P and R act in opposite directions. Okay, and vertically, and Q and S act in opposite directions horizontally. So which information about the magnitudes of the forces is correct? So P is less than R, S equals Q, okay, blah 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 blah. So there is something you should know about pressure. Actually, perhaps two things. The first is that pressure acts in all directions. Yeah, so actually pressure is acting in all directions on this sphere, but they've only shown 4 arrows. So that's their simplification, or their question in this paper. And the second thing you should know is that pressure of the liquid actually increases with depth. All right, so you can actually do an experiment. You can take a glass or a mug and fill it with water, or perhaps a more viscous substance if you want, but like water, and then preferably like perhaps a tall glass or mug, and also tall fingers. But then you just put your finger inside that slowly, and then you can feel actually that the pressure on your finger increases as you put it more inside the mug. So that proves kind of, well, experimentally, that the pressure of the liquid increases with depth. All right. So then, if we see P and Q and R and S, so the pressure at R should be like so that means that if this is a force actually, so then that means that P is less than R, because P is more above, whereas R is below. So P is less than R, P is not equal to R. Okay, so we also already cancel out C and D, but then P is less than R, P is not greater than R actually. Okay, we can cancel that out. But then S equals to Q, because they are at the same level, so force S is equals to force Q. But then the force which is due to the pressure of the water below is more than the force which is due to the pressure of the water above. Yeah, force is pressure over area actually. So um you know if the I suppose my statement force due to the pressure, that statement was kind of incorrect, but the point is that force and pressure are related, because they're if you assume the area is constant, then the pressure, as the force increases, the pressure increases. So that's the thing. So if the pressure is more as the depth increases, then the force will also be more as the depth increases. That's kind of the point of what I'm trying to say, although my words tend to be very convoluted, but that's my point, that the pressure at R is greater, hence the force at R is greater. The pressure at P is less, hence the force at P is less compared to R, and compared to S and to Q actually, because S and Q are also below P. And S and Q, because they're at the same level, so the pressure is the same there of the water, and also the force on the sphere is the same there as well. So S equals to Q, S equals to Q. P is less than S. That is also true, but then because they stated that P is equal to R, that's why we had to cancel out the option C. Okay, so B, C, and D are out, and A is the correct answer. Okay. Question number 14. The first column in the table gives 4 examples of work being done. The second column gives more detail of the action, so which row is not correct? The first example is a girl dives from a diving board into a swimming pool. Okay, so she's diving down. Work is done by the girl against the gravitational field as she falls. Okay, so I feel like A immediately is the one that's okay. So this is not correct. So I feel like A should immediately be the answer. Why? Because what is the definition of work done? So work done is the force applied, right? And then multiplied by the displacement in the direction of the force, actually, right? In the direction of the force. So that's the work done on. So work done. But then the gravitational field is defined also as downwards, and the girl, she's also falling downwards, right? And we're on Earth. So, the gravitational field is downwards, and the girl is also falling downwards. Um, so the thing is that she is not going against the gravitational field. The work done is not work done against. It's actually work done on, or work done in the direction of the gravitational field, basically. So it's work done on the direction, or like in the direction of the gravitational field. So then A immediately should be wrong for that reason, because the girl is not falling upwards or flying or something. No, she's falling downwards in the same direction as the gravitational field. So A is wrong for that reason. As for B, we can look at the other options, although I already got the answer technically. A man pushes a car along a level road. So this is the car that he's pushing, and then work is done by the man against friction. That is obviously right, because obviously the road is kind of bumpy and stuff, like it's not a very ideal road. What is ideal in life anyways? So there will be friction while the man is pushing, right? So therefore B is right. As for C, an electron is accelerated towards a positively charged plate. Yeah, work is done on the electron by the electric field of the plate, right? So let me think. Yeah, actually, this is the same thing, right? Because obviously, again, F equals ma, I should perhaps state. So then acceleration is accelerated towards the positively charged plate. Acceleration is towards the plate. That means it's the force on the electron is also towards the plate, and the motion of the electron is also towards the plate. So if the force is in the direction of the motion, the force is in the direction of the displacement as well. I mean, the point is that this is not work done against, right? Work is not done against the electron, but like work is done on the electron by the electric field of the plate. That is correct. Although, I suppose electric field is defined from positive to negative, but then that's for a positive charge, but here we're considering an electron, so that it's correct basically, because the force is towards the positive plate, the direction of motion of the electron is towards the positive plate, and obviously if the direction of the motion is to the positive plate, then the displacement is towards the positive plate. It's very, very correct to consider, and it's acceleration anyway, so we can tell that the force is in this direction. So C is also going to be correct for that reason. So piston is pushed outwards as a gas expands, and work is done on the atmosphere by the gas. So, I mean, if you consider the opposite scenario, so if the piston is pushed outwards means the gas expands. So then, if you consider that the gas compresses, then in compression, you have work being done on the gas by the atmosphere, right? Because the gas is compressing. Work on the gas by the atmosphere. Obviously, in the opposite scenario, then, if the gas is expanding, right, then that means that work is being done on the atmosphere by the gas. I mean, that's kind of the definition, but if you think about it, it actually does make sense as well. So then D is also going to be correct. So then A is the one that is incorrect because the girl is going in the direction of the gravitational field, actually, right? So that's why. Yeah. Yeah, so question number 15. A steam turbine is used to drive a generator. The input power to the turbine is Pi and the output power is P naught. The power loss in the turbine is PL as shown below. So what is the efficiency of the turbine? So we know that efficiency is a symbol for efficiency actually, eta. I mean, you could have a symbol for anything really as anything, but anyways, that's not the point. Efficiency is going to be the useful power output over the total power input, right? So it's simply then going to be, so you have the output power PO or P naught, I don't know, PO, I suppose PO, divided by the total power input, so that's going to be PI. So that is your efficiency, all right? And so that is just option D. So that is your answer. So question 16, a constant force pushes a block along a horizontal frictionless surface. Then the block moves from rest through a fixed distance. So what is the relationship between the final speed v of the block and its mass m? So I see a lot of square roots and stuff like that. So I would assume that the equation we're thinking about is probably the one that, kinetic energy equals half mv squared, right? That's quite a common equation we use to relate mass and, well, volume. Yeah, why would we keep saying volume? Final speed v. Okay. So then we can rearrange this to have, I suppose, velocity as a subject. So 2ek by m then equals to v square. But then they said that it's a horizontal frictionless surface. So that would probably mean that, you just because according to Newton's first law anyways, like an object will remain at rest or keep moving at a constant velocity unless acted upon by a resultant force, net resultant force. And like it's a horizontal frictionless surface, you have the law of inertia, right? So my point is that, what nonsense am I saying actually? Never mind. My point, anyways, is that it's frictionless. I have to consider energy, not Newton's first law, I think. Yeah, that's a better way to think of it, yeah. So a horizontal frictionless surface, so then that means that there's no change in energy because there's no friction, right? So then you are going to, actually that is Newton's first law. Yeah, because the velocity is changing. Yeah, right. I was, yeah. With the law of inertia would apply, I suppose, of course. But the point, anyways, that I was trying to prove is that the kinetic energy does not change because it's frictionless. Okay, never mind the words. Then we have basically then that v square is directly proportional to 1 over m. Okay, because I'm assuming this is just a constant. So I'm assuming that v square equals to k over m. So I'm just taking 2ek as a constant. V square is directly proportional to k over, 1 over m. And then I don't see any v square here, so I'm just going to square root both the sides. And so I get v is directly proportional to 1 over root of m. Is that an option? That is an option. That's great. Yeah, so the kinetic energy is constant because it's a frictionless surface and it's just the block is moving, just moving. Actually, no, never mind. I mean, really, the block moves from rest through a fixed distance, okay? But I would assume it's a constant force. Oh, yeah, so then the law of inertia, which is the Newton's first law, would not apply, because you do have acceleration in that case if you have a constant force being applied, I suppose. But then it is a horizontal frictionless surface though. So then if it's frictionless, you wouldn't have loss of kinetic energy, would you? I think. See, this is just proving to me how much I've forgotten about basic physics. Anyways, again, guys, if I've said anything wrong throughout this video, please comment below, because I do feel I might have said something wrong. I don't know. Anyways, question number 17. I mean, at least we got the correct answer, and I'm pretty sure we do have to use this equation. So yeah, but anyways, a man has a mass of 80 kilograms. He ties himself to one end of a rope, which passes over a single fixed pulley. He pulls on the other end of the rope to lift himself up at an average speed of 50 centimeters per second. So what is the useful power at which he is working? Yeah, so there's a pulley, and there is a man who has tied himself to a rope, and I do not really know why. And I hope he is not dead. Anyways, the point here is that he has a mass of 80 kilograms. And we also know the average speed at which he is pulling himself up, right? I mean, yeah. So then his weight is 80 kilograms. That means his kilograms times, well, the gravitational constant, not the gravitational constant, sorry, the acceleration of free fall, or the acceleration due to gravity. See, I should really revise my physics more. But anyways, W equals 80g, so that's the acceleration of free fall. If I feel like I might have said gravitational constant during this video, but then that's actually G, capital G, right? That's different. That's an A2. Anyways, the point is then, of course, suppose it's average speed, so that means when he's getting pulled up, that's also going to be 80g. So that's not W. That 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 that's the force with which he's pulling himself up. But then we know also what is the formula for power. Power is the work done per unit time. Then work done, we can write that as force times the displacement in the direction of the force, and then divide by time. And the displacement time, we can rewrite that as force times velocity. So now we know the force because that's mass times acceleration. So we have MAV as the formula for power, because the mass is 80 kilograms. Then we know his acceleration. Yeah, so acceleration is going to be the acceleration of free fall, as I mentioned, because MA over here is being considered as the weight, right? So his weight, because he's an average speed of 50 centimeters per second, so his weight is basically the force with which he's also pulling himself up, right? And so if you have 80 kilograms times the acceleration of free fall, which is 9.81 meters per second squared, and times the velocity with which he's pulling himself up. Actually, let me just erase this diagram, although kind of reminds me of Hangman, but more important to do physics right now. 50 centimeters per second, and then we just have to convert the centimeter to meter, so I'm going to multiply. So then you have 1 meter having 100 centimeters, so I'm going to multiply by 1 over 100, or you could say divide by 100, I suppose, or multiply by 10 to the power of minus 2, whatever you want to say, as long as you understand what you are doing. So then that's going to be 80 into 9.81 into 50 into 1 over 100, and that gives me an answer of 392.4 kgm square s to the minus 3, which is the same as, well, I'm still going to say watts because that's a unit of power, but that would be the thing. Yeah, so now they've given me kilowatts, so then I'm just going to move this 3 decimal places to the left. It's going to be point. So basically, if you want to, you can just say 392.4 times 10 to the power of minus 3. That's kilowatts. And then 0.3924 kilowatts then. and that's approximately to two significant figures, it will be 0.39 kilowatts, and that's justified because this is to two significant, that, I mean, that's, you can assume it's to two significant figures. I suppose the last digit is 0, so it's kind of debatable, but then, let's assume that 0.39 kilowatts is the answer anyways. So that is your answer. Okay, now, so just erase this stuff. All right, now two wires with the same Young modulus E and cross-sectional area A but different lengths L are subject to different tensile forces F. The extension E of each wire is the same. The column headings in the table show 4 different quantities. Which quantities have the same value and which quantities have different values for the two wires? Okay, so they are talking about the Young modulus. So let's just find that. So Young modulus denoted by the symbol E is actually the stress over the strain, and the stress is actually the force applied per unit area that causes some sort of deformation, right? Because we're talking about wires and stuff, springs and blah blah blah. So then actually, because it has that definition, so it has the same units as pressure, obviously, but then the point is that stress is actually F over A, force per unit area, that causes deformation, and then it's also called as tensile stress, I suppose, in this case. Its symbol is sigma, I suppose. I mean, well, what really has symbols in sigma? I suppose mathematics is more rigid about symbols as compared to physics, but yeah, my book had that symbol, I think. And strain, on the other hand, is how much something deforms or changes shape compared to its original length. Like, yeah, so it's actually a ratio then. So strain, which is denoted by the symbol epsilon, is actually the ratio of the extension. So this is stress, by the way, and this is strain. So strain is epsilon, is the ratio of the extension to the original length. So you could say it as delta L over L naught, or you could also denote it as, I mean, in this case, I'm just going to take the delta L. I mean, you could also denote delta L as E as in extension, and or as X as in like just something X, and then L naught. You could also just write L, I suppose, if you're considering that. I mean, just physics is not that rigid about symbols really, as compared to mathematics. So I'm just going to say that extension is X and original length is L, just so that I have easy variables, I suppose. And so strain is going to be X over L, okay? So my Young's modulus E is then the ratio of stress, like stress to strain, I suppose, is, or stress divided by strain. Yeah, so the ratio. It's a ratio as well. And, well, I mean, technically, the Young's modulus has a unit because stress is a unit of Pascal and strain does not have a unit. So then the Young modulus has a unit of Pascals. So does that mean it's a ratio or does it mean it's not a ratio? I suppose. But anyways, it's stress divided by strain, okay? And then you just rearrange this. So you get F over A and then multiplied by, you could say, or actually divided by, let me do it a bit more clearly. Divided by X over L, and that becomes F over A into L over X. So you get that the Young's modulus E is equals to FL by AX. Okay? I'm just going to erase this part of it a little bit. Okay. So then, let me just rearrange this equation. Actually, never mind. I stated that I kept it as X, but then I saw that the question has actually used the extension as E. So it's better to just use E in that sense, I suppose. It doesn't really matter as long as you understand what you're talking about and can make the examiner understand. But MCQs, anyways, they're MCQs. You just fill in the bubble sheet and stuff, right? So you don't need to show you're working as such. Although it's good to work methodically, but then again, it depends on how much time you have. Anyways, FL by, so E equals FL by AE. The first ratio they want is FL by E. So let me just take FL by E and then my A goes to the other side, or if you multiply A on both sides, you could say then FL by E is equals to EA. Now my Young modulus was the same, and my cross-sectional area was the same, right? Because they stated that it was the same Young modulus and same cross-sectional area A, but different lengths L, different tensile forces F as well. Okay, that's too much highlighting. Oh my gosh. You get the point. Yes, I hope, at least. Okay. So then my ratio FL by E is going to be the same. Why? Because my EA is the same, because Young modulus is the same, and the cross-sectional area is also the same. Yeah. Then let's look at the next ratio, which is AE by L. So I'm just using this equation for everything. Okay. Let me just highlight this equation. Perhaps this is better, so you understand that this is the main like reference equation. And then we have AE by L. So let me just flip this, I suppose. So I'm just going to make it 1 over E is equals to AE by FL. Okay, so I'm just flipping this equation. So I'm dividing, like 1 divided by E equals to 1 divided by FL by AE, then that becomes AE by FL. Okay, and then I'm going to make it as, I'm going to take F to the other side, or multiply both sides by F, so then you get AE by L. And again, I just now realize that you use capital L than small L, but the point is that you understand what I'm talking about, I understand what I'm talking about, so that's pretty fine. F divided by E, okay? Now they have different tensile forces, although the Young modulus is the same. So if the Young modulus is the same, but you still have different tensile forces, right? So because you have a quantity that's different for both the wires, like this, which is F, in this equation for AE by L, that means that AE by L is going to be a different for both the wires. Okay, now let's look at the next one, which is E by FL. So for E by FL, I'm going to just multiply both sides by 1 over FL. So I'm going to get E over FL is equals to 1 over AE. And 1 over AE, now my sorry, again, I just, okay, my cross-sectional area is the same for both wires, but my extension is also the same. Actually, they stated that the extension of each wire is the same. That's good. If if the cross-section area is the same, extension is the same, that means 1 over AE is also the same. So that means this is going to be the same, the same, the same. So where do we have 3 ticks? We have 3 ticks here, so then D is going to be the answer. Okay, next question. Two springs, X and Y, stretch elastically. The graphs show the variation with the extension X of the force applied to each spring. So extension is X and force is F. Now, which statement is correct? They're talking about extension, forces, and then the energy stored. Let's talk about an equation. So you see this is a graph of the force applied against the extension of each spring, and the area under the curve is actually going to be the work done on the spring. So the work done on spring, you would also say the energy absorbed, technically, I suppose. Basically, it's, you could say that like the energy absorbed, the work done on the spring, or you could say the strain energy. You could also say again the energy stored, the elastic energy, elastic potential energy, work done by the spring to release the energy. So it's the energy stored, it's work done by the spring to release the energy, so it's the energy stored inside the spring. Anyways, the point is that it's energy. So it's energy, so E. And how do you calculate it? It's the work, like this area under the curve, and this area is actually a triangle, right? And it's a right angle triangle, which, you know, we all know how to calculate right angle triangles, I suppose. It's the base, this is the height, so the base is X, so you're going to have half times the base, which is X. Let me remove this multiplication sign. Half times X times the height, which is F, right? So it's half Fx. Let me write that as half Fx. That just sounds better. Half Fx. And then what else can we say? We can say that we already know what the spring constant is, I think. So K equals F of X, right? F over X, sorry. So much calculus that I see F of X everywhere now. After university. Okay, anyways, so K equals F over X, and then you have F equals to kx. Okay. This is the spring constant times the extension, and by the way, this is the technically the okay. I don't know if this the video still looks as smooth as it did, but like my recording stopped and then I had to make a new video, and I might merge them. I hope I can merge them. Anyways, I have F equals to kx, and then I was saying that this is half F, that's the average force, right? So basically you're going from 0 to F, so then 0 plus F by 2 is equals to half F. That's another way you could think of it. So then you have the work done is equals to force times the displacement. So then your force is actually the average, because it's a triangle. So half F, and then your displacement is actually the extension, so x. So half fx. That's another way you could think of it, or you could think of it as area under the curve. So it's half fx that way because it's a triangle. So that's two ways you could think about it, and technically they're the same way. I mean, in essence. Nevertheless, this is the one equation that you have. Then the other thing is you could substitute kx in the place of f, so you get kx times x, so you get half kx squared. Okay, so now that we have done this, let us look through the options. When each spring is given the same extension, the energy stored in y is 4 times the energy. I suppose before I do this, it's worthwhile to also calculate the spring constant. So k is equals to f over x, right? So it's 20 newtons per 10 divided by 10 centimeters. So it's 2 newtons cm to the minus 1. And then over here you have um, spring y. So that is going to be k, let me say this as kx, ky is going to be 80 divided by 5. So that's going to be 16 newtons per centimeters. Okay. Anyways, when each spring is actually, should I change this to meters? I mean, I don't think we really need to for this problem, but I feel like it's just good practice. So I am going to convert this to meters. So 1 meter, so what, 1 centimeter, 100 centimeters actually in 1 meter. So that's just going to get multiplied by 100. So we get 200 newtons per meter. And then here, using the same logic, you would get 1600 newtons per meter. Okay. Anyways, when each spring is given the same extension, the energy stored in y is 4 times the energy stored in x. Okay, so then I suppose we could set up a ratio. So the energy stored in y is 4 times the energy stored in x. So then ey over ex is equals to half times kx squared, half ky times x squared divided by half kx times x squared, and then they have the same extension, so I can cancel out x squared and I can cancel out half as well. So it's the ratio of their constants basically. So it's ky over kx. This is a subscript, by the way. I don't know if it's clear or not, but yeah, so it's going to be 1600 over 200. So that is actually 8 rather than 4. So then A is wrong. Okay, as for the question, option B, you have the energy stored in y is 8 times the energy stored in x. If each spring is given the same extension, and that's what I got actually here, that means B is probably right. If I see the other two options, however, just to check, so then I have when the same force is applied to each spring, yeah. So Ey divided by Ex then is equals to, I'm going to use this equation because they're talking about force rather than extension only. So half Fx divided by half Fyx divided by half F of x. Okay, so how F that goes, yeah, that gets divided, and then, well, there comes the problem, I suppose, that I can't just assume their extension is the same, can I? So half times E by E, same force is applied, so the ratio is the ratio of their extensions. So I suppose we could consider of like could we do something like, I don't know, x is equals to f over k technically. So instead of considering this, I could consider half times f over k technically. I could rewrite this equation as that, and then I would get half times f squared over k. And so if I substitute this over here, then I get half times f squared over k divided by ky over half f squared over kx. So then half gets divided, f squared gets divided. So let me just write it over here. I get 1 over ky divided by 1 over kx. I'm not sure if I'm doing this right, by the way. I really don't know. Point is, I've already gotten the answer, so I don't really need to do this, but like, I don't know why I'm doing this, honestly. Anyways, let's just do it. 200 over 1600, yeah? So that comes out to be 0.125, or basically 1 over 8, the opposite of that ratio, I suppose. So 0.125, yeah? Or the inverse of that ratio, I should say. Anyways, 0.125. That is obviously not the correct answer, so yeah. Because that says 4 times, that says 8 times. So the answer is B in summary, okay? Yeah. Question 20. The diagram shows the force extension graph for a steel wire up to its breaking point. So assume that that's its breaking point. Yeah. Now, what is the best estimate of the work done to break the wire? So, as I already mentioned, for a force extension graph, the area under the curve is actually the work done, right? The work done by the spring to extend it, or rather the work done by the spring to release the energy. The point is the work done. So then, yeah, I should really revise my physics definitions, I suppose. Better. But the point is, it's going to be work done. So what we can do is find the area. So we can just use our, basic, I forgot what branch of mathematics is it? Is it called like geometry or what? But like, point is, you guys know how to do it. So who cares about names, right? So I have this trapezium firstly. I think I'll use a highlighter option. So this is a trapezium, yeah. I'm not shading it all fully in because that's kind of annoying. And then I have this triangle. Okay. So then I'm going to find the area of the triangle first. Because why not? So triangle area. This is in millimeters, by the way, note that. So this is going to be 1, 2, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. It is perhaps a bit overlaid. 8, 9 already. So then you're going to have 1, so 1 millimeter, and then I'm going to convert that to meters. So then you have 10 to the power of 3 millimeters in a meter. So 1 meter has 10 to the power of 3 millimeters, right? And then I multiply that by, let me just write it down. I'm just going to write it on the left side because I don't have space, okay? So A is equals to a triangle equals to this expression. So then you have this multiplied by the base. So that is the base actually, sorry. That's the base, and then height is 200. That's the force. So then you're gonna get the answer of this as 200 divided by 1000. That's kind of, actually, why am I using a calculator for that? I don't know. I think I did something wrong. Yeah, that the thing I did wrong is is that I forgot how to calculate the area of a triangle because it's not base into height, because base into height is actually a parallelogram. When you divide a parallelogram into two equal halves, you get a triangle. So this should actually be multiplied by half. Yeah, you should never forget your basic stuff. Anyways, this is going to be 0.5 into 200, and then basically I got 0.2 before, right? So that's going to be 0.1 joules because that is energy work done. All right, and then my area of the trapezium. The silly mistakes are annoying, honestly. Half h times a plus b, but they happen. Then you're going to have half multiplied by the height. So the height is 10 minus 1, so that's 9. So 9 into 10 to the power of minus 3 meters, because it's in millimeters. And then you're going to multiply that by a, so the area of the a plus b. So a and plus b are the parallel sides lengths. So a is 200, b is 250. And so we're just going to calculate this out. 0.5 into 9 into 10 to the power of minus 3 into 200 plus 250. So we're going to get 2.025 joules. And so I'm just going to add these two areas to get the total area under the graph. All right. So the force extension graph. So yeah. So the area is going to be 0.1 plus 2.025, which is 2.125 joules, and that is approximately 2.1 joules correct to two significant figures. So then my answer is going to be A. Yeah. That's the first 20 questions done. So I will take a break and then come back to this. Okay, so question number 20. Which statement about electromagnetic waves in a vacuum is correct? Okay, so electromagnetic waves in a vacuum. So, I mean, okay, so amplitude is inversely proportional to velocity. But I mean, I don't know if they're talking about the velocity of the wave or the particle velocity, but like basically, this is the wave equation, right? V equals F lambda, but then for electromagnetic waves, it's anyways C equals to F lambda because, we already know that in a vacuum, especially, that the speed of the electromagnetic wave is going to be the speed of light, which is 3.0 into 10 to the power of 8 meters per second. So, I mean, if you're assuming that they're talking about the wave velocity, as opposed to the particle velocity, because particles are obviously moving, but then the wave, the wave velocity will be 3.0 to 10 power 8 meter per second, like constant, kind of, and so we can cancel out option A for that reason, and option D, because again, velocity is proportional to wavelength. And as for frequency is proportional to wavelength, yeah, like because if the wave velocity is constant, then f lambda, those are proportional because this is a constant. So then frequency is inversely proportional to wavelength. That is true. As for this one, intensity is proportional to amplitude. That is wrong. It's actually that intensity is proportional to amplitude squared. So I'll actually list a video for the derivation of this relationship in the description, which I found quite useful. But um, roughly how we derive it is like we know that intensity is basically the power per unit area, and then power is basically the work done per unit time, right? So then that means we could kind of say that power is directly proportional to kinetic energy, right? I mean, the reason for that is because if you like, because work done is a type of energy, kinetic energy is a type of energy. And then what happens is EK, kinetic energy, equals to half mv squared, right? And this is the particle velocity, I think. So then you get that the kinetic energy is directly proportional to v squared, and um like if you're assuming the constant time, like one specific time interval, I suppose, and like depending on the amplitude of the wave, you can also say that the velocity is directly proportional to the amplitude, and it says amplitude, not area, it's amplitude. And you know, I mean, yeah, so the velocity of the particle depends on the amplitude. And then what we can say is that because velocity is directly proportional to amplitude, then that means the kinetic energy is directly proportional to the amplitude squared. We can make it like that. And then, because we know that the power is directly proportional to the kinetic energy, so then the power is directly proportional to the amplitude squared. And if we're assuming again a constant area, then that means that the intensity is directly proportional to amplitude squared. But again, I explained it roughly. I list of videos, so there it's explained with some graphs and stuff as well. So I really like that video actually. It's a nice video. But basically, the relationship is not that intensity is proportional to amplitude, it's intensity is proportional to the amplitude squared. Okay, so basically the answer is going to be B. Frequency is inversely proportional to wavelength, because anyways in a vacuum you're going to have the velocity of the wave as constant, which is 3.0 into 10 power of 8 meters per second. Okay. Okay, so question 22. A transverse wave travels along a rope. The graph shows the variation of the displacement of the particles in the rope with distance along it at a particular instant. So then, at what distance along the rope do the particles have maximum upwards velocity? So the maximum velocity, because anyways v equals to, okay, so this is displacement against distance actually, so they're just showing the rope. But then anyways, you're going to have maximum velocity at this point where it's like that, and then like where you have maximum gradient kind of, even though it's a displacement distance graph I suppose, but you do have it like that, right? And yeah, so then I mean it's kind of obvious. It's kind of like, you know, you go down a hill and then up a hill and down a hill and up a hill, and of course like the rope is moving like that, right? So I mean, even though technically the velocity is not the gradient of the graph, but then if you think of it in that sense, it still does make sense that you would have maximum velocities at these points, like hills or like, you know, going up and down. You would have maximum velocity here, and I suppose maximum tension there. I don't know, like not tension, but like, you know, maximum negative velocity then. Yeah, but anyways, let's. I mean, well, that is actually another question where we have to now see that. Well, if I, because this is at an instant of time, and then now if I shift the wave like that, because you know it's moving along this direction, so that means after some like another at another instant, then it's going to have shifted like that, right? And so that means that this is moving up, this is going down, down, and that is going up. And maybe I'm not drawing it very accurately, but the point, you can see my point, right? Yeah, I should really revise my physics, but my point is this. So if they're asking about maximum upwards velocity, then here the graph is going upwards, here downwards, here upwards, here downwards. So then what options do I have? 0.5, 1.0, 1.5, 2.0. Okay, so 1.5 was downward, so I can cancel that out. 2.0 was upward. No, that's okay, sorry. 2.0 is here actually. Never mind. Why would I have it at a peak? That is not nice. As for 1.0, again, it's at a peak, so I'm going to cancel that out. And then that means probably 0.5 is my answer, and yes, that is where it's going upwards. So that is the answer. Yeah. Oh. Question number 23. A trace is shown on the screen of a cathode ray oscilloscope, CRO. The time base setting is 2.5 milliseconds per centimeter and the Y gain is 2.0 volts per centimeter. So what is the frequency and the amplitude of the waveform displayed by the CRO? Okay, so the amplitude is just going to be, because okay, so the Y gain is 2.0 volts per centimeter, right? So each box, like box vertically is 2.0 volts per centimeter. So if there, this is the amplitude, right? Because that is my equilibrium line, and so that is going to be two boxes, so that's 2.0 volts per centimeter times 2.0 centimeters, because there's like this is 1 centimeter, right? So then I'm going to get my amplitude as 4.0 volts. Okay, so that's that. And as for the frequency, well, frequency is the number of oscillations per unit time of a point in a wave. Anyways, you can write that as 1 over time period. So 1 over, so the time base setting is 2.5 milliseconds per centimeter. Then we can multiply that by 10 to the minus 3 to make it seconds per centimeter. You want me to, I guess I'll write that in a better way, I think. We can write it as 1 second has 10 to the power of 3 milliseconds, and that's why I multiply by 10 to the power of minus 3 before. And that's the time base, but then what do we have to multiply that by, because that time base is 2.5, and then what is the time period? So we can see that this, if I take this as my starting point, then one wave is being done at that point, so that's 1.5 boxes. So that means times 1.5 centimeters, because each box is 1 centimeter. So yeah, and then I'm going to get this as 1 over 2.5 into 1 over 10 to the power of 3 into 1.5. That is going to give me 266.6 recurring s to the minus 1, which is the unit of frequency, or hertz, basically, it's equivalent. And that is approximately 267 hertz, right? Correct to 3 significant figures. And so it's either C or D, and because I have 2 ticks on C, so C is going to be my answer. Okay, so next question. A high-speed train approaches a stationary observer at a speed of 80 meters per second. The train's horn emits a sound of frequency 250 Hz. The speed of sound is 340 meters per second. So what is the observed frequency of the sound from the horn? So for this, we can use the Doppler effect, the Doppler equation. So F naught, or F F observed equals to the frequency of the source times the velocity over v plus or minus the velocity of the source. And they, okay, wait, so the speed is approaching this, the train is approaching the observer, right? So this is the observer, that's the train, and it's approaching the observer. And so that means that the observed frequency is going to be becoming greater compared to the source frequency, right? So the observed frequency is becoming greater because the train is approaching the observer. So it's going to become louder and louder as it approaches the observer. So that means that if you consider this fraction of v plus or minus vs, then if this is increasing, then this must decrease, because if you consider something like k equals a x or whatever, then if this is a constant, if you assume it, I mean, then as a increases, then x decreases, right? Because two quantities that are multiplied are inversely proportional in that sense. I mean, roughly you can say here that thus if f naught is increasing, then this v plus or minus v as fraction must be decreasing. And because it must be decreasing, then it's taking, instead of taking the v plus vs version of this formula, you're going to take the v minus vs version of this formula because they're moving towards each other. Yeah. So then let us calculate the observed frequency. And so the frequency of the source, which is the train, is 250 hertz, and then the velocity of the source, the speed of sound is 340. So that's the one we should use. Yeah, that is the medium, 340 meters per second divided by, again, the speed of sound, 340, minus the source's velocity, which is the train's velocity, so 80 meters per second. So this cancels out and you get the unit in hertz, obviously. And so let's do this calculation. So 250 into 340 over 340 minus 80. So you get 326.923 dot 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 dot. So it is approximately 330 hertz, correct, to two significant figures. Yeah. So that is closest to option D. Therefore, I'm going to say that option D is the answer. Okay, so then which row shows a correct frequency in hertz for each of the four principal radiations? Yeah, so this is a very much memorization based question, and you can probably find the chart or the diagram somewhere, so you can do that. And microwaves, I mean, microwaves have frequencies from the magnitude of 10 to the 8 to 10 to the 12 hertz, I think. So 10 to the 10 is the nearest option for microwaves. And so the answer is just D, basically. But it's better if you can verify it with more and more, if you know the diagram of like the frequencies, and then obviously using the frequencies you can calculate the wavelength. So you really just need to memorize like the frequencies for each one, like the frequencies of radio waves, microwaves, infrared, visible light, ultraviolet, x-rays, gamma rays, and then using that you can find the wavelength because c equals to f lambda. Or you could memorize the wavelengths and then use that to calculate the frequencies. So that's one thing. And well, I suppose microwaves, radio waves, I suppose like technically the wavelength is easier to memorize in a way. So yeah, like microwaves, they have like 10 to the power minus 1 magnitude meter. And then I don't know. You can look at the chart. Anyways, the answer is D. Okay. So then let's go to the next question. So a pipe of length 100 centimeters is open at both ends. A loudspeaker situated at one end of the pipe can emit sound of different wavelengths. At which wavelength can a stationary wave be produced in the pipe? Okay, so for the first harmonic, or the fundamental, again, because it's open ended, well, I mean, you have like, well, I'm not very drawing it very well, but like something like that. Like both ends are open, yeah, as I said that. And so you have, this is half of a wavelength, right? So half of a wavelength, and so half lambda is equals to L, right? And so therefore here in this case lambda equals to 2L. And then if you had another case, like the next case after that, like the second harmonic, then you would have this like that, right? So now you have L is equals to, well, you have basically one full lambda in this case, because this is one lambda and then you have these two half lambda, so that becomes half lambda. So then half lambda, I'm sorry, my mistake. So this is half lambda and these two are half lambda, right? Or you could consider it as if you divide this into two halves like that, so then this is half lambda, which is the same case as this one that we had here, and then the other one is also half lambda. So in total you have lambda. All right, so L equals lambda here, so then lambda equals L, right? And then if I consider the third harmonic, then I have this, right? So there I have half lambda plus half lambda plus another half lambda, yeah? So then that becomes L equals 3 by 2 lambda, because it's one lambda that was originally there plus another half lambda, so that becomes 3 by 2 lambda. So basically every time you're adding another half lambda, if you have both open ends or both closed ends. And then here then lambda equals 2L by 3. Anyways, the point here is, okay, so now I have these equations, so let me substitute lambda, the length, I suppose, because they said at which wavelength can a stationary wave be produced in the pipe. Yeah, so I mean, if I take 100 as lambda and substitute it to find which wavelength I actually need, then I get half times 100 equals 50 centimeters. That is a probable option. So basically, I am taking the length, yes, but then I'm using that to find what wavelength is required, if you get my point. But like, yeah, it's 50 firstly, so I guess A would be right. But then if I look at this one, then it's 100. And then if I look at this one, then it would be 3 by 2 into 100. So that would be 150. Wait, I think I'm doing something wrong, because obviously you can't have two options as correct. Perhaps there is a better way to do this. Wait, think about this. Erase that, and I'll not assume anything for now. But what we could do is, because we have figured out that this is just increasing by half each time, so half lambda equals L, then L equals lambda, then L equals 3 by 2 lambda, and so on. So you get like 4 by 2, 5, which is 2, and then 5 by 2, 6 by 2, and so on. So then I could just take the ratio of L over lambda and see whether it is a multiple of, like, like half. Yeah, so that seems like a better strategy than what I had originally done. And yeah, I really should revise my physics, is what I've learned today. But anyways, let's do that for each option. So for option A, we have L over lambda as 100 over 50, which is equals to obviously 2, and 2 is basically 4 over 2, right? So I think it is a valid option. As for B, we have 100 over no, it's not writing. Yeah. 100 over 75 as the ratio of L over lambda, because L is 100. That makes much more sense, actually, now that I think of it. Yeah, I don't know what I was saying before. Anyways, this will be 4 over 3, which is not a multiple of half. Yeah. N times half, I mean. N being a whole number. Okay, and then for C, we have 100 over 150 as the ratio, and that is going to be 2 over 3, which is not a multiple of half. As for D, D is 100 over 300, that's the ratio of L over lambda that we are finding in each case, because we have seen over here that L over lambda equals half, L over lambda equals 1, which is um, um, or 2 over 2. Yeah, 1 is 2 over 2, yeah. And then we have L equals, L over lambda equals 3 by 2, and so on, 4 over 2, 5 over 2, 6 over 2, and so on, yeah. And so 100 over 300 is going to be just 1 over 3, which is not a multiple of n times a half. So the only one that is a multiple of n times a half is this one, which because it's 4 times a half, right? So A is the correct answer then, because that is a multiple of lambda, which is the trend we saw for both ends open or both ends closed in harmonics. Yeah, so that is the answer, I think. A. Okay, let me just erase this stuff and then go to the next question. Okay, so let's go to question number 27. Monochromatic light is incident on a diffraction grating and a diffraction pattern is observed. Which row shows possible effects of replacing the grating with one that has twice as many lines per millimeter? Okay, so if you have twice as, so if initially I had these lines, but then now I have twice as many lines, that means that because my grating spacing has basically decreased, right? Because what's my diffraction grating equation? It's n lambda equals d sine theta, where n is obviously an integer value, like the number of slits, or it's the order basically, and then lambda is obviously the wavelength, and then d is the grating spacing, which we have now changed because they said we have replaced the grating with one that has twice as many lines per milliliter, so millimeters, sorry. And so initially it was this, but then now it's much tinier. Yeah, so it's much tinier. And so, and then sine theta is obviously theta being the angle for the nth order maximum. And if I rearrange this to make the grating spacing the subject, so n lambda over sine theta equals to d, right? So then, I would assume lambda is a constant, and they're asking me to find determine whether what decreases, like if the number of orders of diffraction visible, which is n, and also about the angle between the first and second orders of diffraction, which is I guess we could say, because technically that is not theta, because the theta is the angle for the nth order maximum and start from the 0th order, but then obviously if theta increases or decreases, then the angle between the first and second orders of diffraction would also decrease. Yeah, so anyways, nevertheless, would also increase if theta increases, or decrease if theta decreases. I hope you get what I'm trying to say. Anyways, the point here being that so I could draw this as well. So if I have 0, 1, 2, and I mean technically I should probably draw a screen as well, right? And the point being that this is also 1, but from the opposite direction, and 2, And so if this is theta 1 and theta 2, right, then they're talking about the angle between the first and second orders of diffraction, which is going to be the angle between the first and second orders, theta 2 minus theta 1. It's going to be this angle. That's not really theta, but like if theta increases, like if theta theta if obviously theta being like theta 1, theta 2, theta 3, etc., if that increases, then this angle alpha will also increase, is my point, if you get what I'm trying to say. I hope I'm not confusing things too much, or I'm not saying something wrong, I hope. Anyways, the point being that if the grating spacing has decreased, as it has, as in the question has mentioned, then, well, then because d and sine theta are being multiplied, that means that this quantity would probably be increasing, and you're assuming that lambda is constant, by the way, and because d and n are like technically divided, if you write it like this, d over n equals lambda over sine theta, and so these are directly proportional, or not really directly proportional, but like, I mean, they're divided, so then they increase and decrease together, basically. So then if d decreases, then you would expect n to decrease as well. So n would, you expect it to decrease, whereas sine theta you expect it to increase. And so if sine theta increases, then that implies that theta will also increase. Okay, so then your answer is going to be where there are two ticks, so that's going to be B. Okay, the next question. Monochromatic light of wavelength lambda is incident on two slits, S1 and S2, a small distance apart. A series of bright and dark fringes are observed on a screen a long distance away from the slits. The nth dark fringe from the central bright fringe is observed at point P on the screen. So which equation is correct for all positive values of n? Yeah, so this is a nth dark fringe. And what does a dark fringe imply? Well, you have two types of interference maxima, obviously. So you have constructive interference maxima. So this is basically like Young's double slit experiment. So for the constructive interference maxima, you have bright fringes where they meet perfectly in phase with each other. And then you have dark fringes where there's destructive interference. And these maxima are where there is perfect, like they're perfectly out of phase with each other, right? And so you get the dark fringes. So what that means is that because there's destructive interference where the two waves cancel to give reduced or zero amplitude at a point in space, but then because it's a dark fringe, so obviously you have zero amplitude at that point in space. So what happens is that there's one wave, and like you have two of these, right? So S1, S2, and then the path difference between them, obviously. And basically that is what these formulae are. So you have S2P minus S1P. So those are the path differences. Yeah. And so like you have this one wave which is like this, and then you have another wave which is like that, right? And so when these two interfere with each other, they completely cancel each other out, if you can see that, because they're perfectly out of phase by 180 degrees, i.e. by pi radians, right? And like if you look at a unit circle, so then basically what that means is that the phase difference that they have, i.e. the angle difference that they have, the delta theta is going to be pi, right? So that the phase difference is going to be pi. And so like if you look at your quadrants, then like if you start from here, then this is 1 pi, and then you get 2 pi, and then you have 3 pi. And the thing is that this interference that occurs, it only occurs at the odd values of pi. Yeah, I don't know what's happening today, honestly, because my recordings keep, yeah, so they're separate now, and so I have to merge all the recordings later. But anyways, so where was I? Okay, so we canceled out those two equations, and now we have the option of n minus half lambda and n plus half lambda. And the question states which equation is correct for all positive values of n, because actually, technically, because n is an integer, so like, usually we think of it as starting from n equals, I mean, equals, it starts from 0, right? So 0, 1, 2, 3, and so on. But then because it's positive, that means you're not considering 0. So it's just 1, 2, 3, and so on. Now, in these two equations, if I substitute the value 1, so if here I put like 1 minus half lambda, then I get half lambda for C, right? But then as for D, if I put 1 plus half lambda, then I get 3 by 2 lambda. And the thing is that over here in my path difference, I start from half lambda, right? Because first you think about half a wavelength, then you think about 3 by 2 of a wavelength, then you think about 5 by 2 of a wavelength, and so on. But then that means that like D must be wrong because it's starting from 3 by 2 lambda with n equals 1. So then D must be wrong, and that is actually the equation if you had started from 0. So 0 plus half lambda, then that would make sense for the destructive interference path difference. But then because you're starting from 1, because it says for all positive values of n, said 1 minus half lambda must be the equation that you use for the path difference, and so C is going to be the answer. Yeah, hopefully that makes sense, I hope. Anyways, let's go to the next question. Okay, so question number 29. A dipole is a pair of charges of equal magnitude, one negative and one positive. The electric field of a dipole is shown below. In which direction does the force act on an electron when at point X? Yeah, so the electron is there. And then the thing is that, well, I mean, firstly, it must be tangential. The force on the electron must be tangential to the electric field line, so we can already cancel out B and C because those are just veering off in a very weird direction. So it's either A or D. The second thing is that the electron is obviously attracted to the positive part of the dipole, so then it is going to be going like that, right? The force on the electron, I mean. So therefore, it's going to be D. That's the answer, not A, because that would cause repulsion, whereas the electron wants to go to the positive dipole. So then the answer is going to be D. Okay? So question number 30. In a uniform electric field, which statement is correct? Letter A. All charged particles experience the same force. Yeah, well, we know that this is the equation, for the uniform electric field, so we would have F equals QE, right? Or perhaps like we could say the defining equation is E equals F over Q over, you can say that electric field strength is the force per unit positive charge or whatever. That's the equation, right? So then that means like if they're saying all charged particles experience the same force, by definition that's kind of wrong because F equals QE and charge Like it's not necessary that all charged particles have the same magnitude of charge, right? So that's not likely. And then all charged particles move with the same velocity. Well, again, we know that F equals ma, so then ma equals to qe. Therefore, a is equals to qe by m, where a is the acceleration. So acceleration also depends on like that not only the charge but also the mass. So then, or the charge to mass ratio. But then that's the problem. So then that means that not all the charged particles will have the same acceleration. And we know that acceleration affects the velocity. So if they do not have the same acceleration, how can they have the same velocity necessarily, you know? So we can also cancel out B. All electric field lines are directed towards positive charges. Yeah, so I don't really understand what that means. Like, isn't it just that, like, perhaps if I have a positive plate and a negative plate, then, like, isn't it going from positive to negative? Or, like, what does the question actually mean? All electric fields are directed towards positive charges. I mean, from here I can see that it's going from positive to negative, not from negative to positive. So I suppose that's wrong. Then talking about positive charges, because say you define it using a positive test charge, but then obviously a positive test charge means that it's going to be repelled from the positive plate and go to the negative plate. So then I guess it should be the opposite if I understand the question correctly. If not, you guys can correct me in the comments. And then that leaves only option D, which says that all electric field lines are parallel, which is true because it is a uniform electric field after all. Yeah, so that's going to be the correct answer. Now let's go to the next question. So, question 31. Two metal plates are at a distance of 30 centimeters apart in a vacuum. A current exists between the two plates consisting of electrons moving at a constant speed of 1.5 into 10 to the power of 6 meters per second. Yeah. And then at any instant, there's always just one electron traveling between the plates. Okay, that's, I guess, a simplifying assumption, perhaps. Now, what is the current between the plates? So, I guess we could just use the current equation. So, current is the rate of flow of charge, right? So, I equals Q over T. And then for an electron, the charge of an electron, so 1.60 into 10 to the minus 19 coulombs, right? And then the time, well, we know that T is basically equal to d by s if you use it in simple terms, right? So it's the displacement divided by this, or the distance divided by the speed simply. So we can take the distance, which is 30 centimeters. So 30 centimeters, convert that to meters. So 1 meter has 100 centimeters. And then divide that by the speed. So that is 1.5 into 10 to the power of 6 meters per second. Yeah, this is divided. So then your meters and meters cancel out. And then you have per second, so that goes to the numerator. So we have coulombs per second, which is the correct unit for current. Coulomb per second, which is equivalent to obviously amperes. So let's do this calculation. 1.60 into 10 to the power of minus 19 over 30 into 10 to the minus 2. And then divide that by 1.5 into 10 to the power of 6. So you get 8.0 into 10 to the minus 13 amperes or coulombs per second. And that is option B. Okay. Next question. Yes. So the diagram shows a portable generator connected by cables to floodlights. The generator produces a current of 10 amps at a constant potential difference PD of 240 volts. The total resistance of the cables is 2 ohms. So what is the potential difference V across and the power delivered to the floodlights? So initially your input power or whatever you want to call it was actually going, well it is, I mean, Vi, right? So then if P equals to Vi, then, okay, so 240 multiplied by 10, so you get 2400 watts initially, right? And then my initial resistance, because we know that V equals IR by definition, right? So R then equals to V over I. Maybe that's the definition. But anyways, the point is R equals V over I. Yeah, and then the initial voltage was 240. Initial current was 10. So your initial resistance was 24 ohms in the generator. And then because the cables had resistance of 1 ohm and 1 ohm, so your resistance decreased to 24 ohms minus 1 ohm for each of the cables. And so you got the new resistance as 22 ohms. Okay, there. So you had 22 ohms resistance. And then your new voltage then would be simply IR. Yeah, and that is going to be 10 multiplied by 22, so that's going to be 220 volts. So you've basically had a voltage drop of 20 volts from 240 to 220. And so our answers are going to be A or B. As for the power is equals to V squared over R, which is going to be 220 squared over 22, right? Which is going to be 2200. Alternatively, you could also calculate this using the formula power equals I square R, where you would write 10 square into 22, which is also 2200. Or you could write it as P equals VI, where you would have 220 into 10, so you would also get 2200. The point is, the power is 2200 watts. Did I write that? I don't know if yeah, the unit is watts, and so this is going to get cancelled. And therefore, you have 2 ticks on B, so B is going to be your answer. Okay? Yeah. Next question. So, question 33. A metal cube with sides of length A has electrical resistance R between opposite faces. So what is the resistance between the opposite faces of a cube of the same metal with sides of length 3A? So resistance, it comes from, like, the resistance to the motion of the electrons, because like positive ions, in the metal, they collide with the electrons and slow them down because they attract them and blah blah. The point being that resistance is directly proportional to length, but resistance is also inversely proportional to area, or perhaps maybe it's better to write that as resistance is inversely proportional to area. So then that means that resistance in summary is directly proportional to the length over the area. And then if we write this as a proportionality without the proportionality sign, and we put a constant, so that constant is rho. So R equals rho L by A. Rho is the resistivity, and the resistivity is unique for every metal. So each metal has its own unique resistivity. Okay, so we can use that fact. So we can rearrange this equation as rho equals R A by L. So then we have R A by L. Okay, and what we can do is we can say that because the metal has the same resistivity all the time, because that's a unique property of a metal, it's a constant. And so what we can say is that, imagine, because it initially had the resistance, electrical resistance R, right? We can say R, and R times the area. So the area of this cube is A times A square. So R times A square divided by the length of it. So the length is A, like because it's a cube anyway, so then A, everything. Length is A, right? So times A, and that is equal to, if you consider the cube of the same metal, because it will have the same resistivity, so this will be equal, with sides of length 3A this time. So let me just keep the resistance of this other cube as X, okay? Because that I have to find. Times, now the same metal with sides of length 3A, so this will become, the area then will become 3A whole square, and then the length will become 3A also, okay? So what happens then is that I will just write this as R A square over A is equals to X times 9A square divided by 3A, okay? And then this gets divided with this gets, sorry, cancel with this. And so you get R is equals to, and then 3 1s are 3 and 3 3s are 9. So that becomes R equals to 3X, which implies that X, which is what we need to find, is equals to, if you just divide both sides by 3, then you get X is equals to 1 by 3 of R. And that is an option, so C. So this new resistance is going out of the other cube is 1/3 of this cube's resistance. Okay. Now the next question. So question 34. A graph of potential difference PD V across the cell against current I in the cell is shown. As the cell reaches the end of its useful life, its internal resistance increases and its electromotive force EMF decreases. So which diagram shows a graph of V against I for the cell nearing the end of its useful life? Okay, so firstly, if I plot if I write the equation for this graph, the thing is that this will be the EMF, right? The EMF, which I'm denoting as E, right? So V is equals to E minus I. R is the equation, because like obviously you start out with the electromotive force, and then as the cell reaches the end of its useful life, so then keeps decreasing and decreasing, and we know that V equals IR, so the minus IR, it decreases by that much, and then that's basically the equation of the graph. So the intercept, I mean, if you plot it as y equals mx plus c, so then you get y equals V equals minus R I plus E. You can rearrange the equation to write it like this. And again, guys, if I'm saying anything wrong, you can tell me in the comments, please. Y equals mx plus c, right? So then your y is v, as you can see, I is here, so it's x, and then your gradient is minus r, and your intercept is going to be the electromotive force, right? So what can I say? So if they're saying that as the cell reaches the end of its useful life, its internal resistance increases. If the internal resistance increases, then that means that the slope increases, right? So if slope increases means that the gradient increases. So it becomes like something like that maybe. So if I look at the options, that's the line of the original graph. This is having a steeper gradient. This is having a steeper gradient. This is having a steeper gradient. That is having not a steeper gradient, so we can cross that out. And so till now I have A, B, or C. As for the next statement, it says that its electromotive force decreases. So if electromotive force decreases, that means that intercept, the y-intercept I should say, the y-intercept also decreases. So it becomes a lower value on the y-axis. Now in A, you have it as the same, so that can't be right according to the problem statement. Whereas in B, the y-intercept is smaller in the new graph, so that could be right because it's this line is steeper, and it's also the intercept is lower, and over here you have the intercept is higher, so that is wrong. So then I'm going to say that the answer is going to be B. Okay, so yeah, now the next question. So a 20 volts DC supply is connected to a circuit consisting of 5 resistors L, M, N, P, and Q. There's a potential drop of 7 volts across L and a further potential 4 volts potential drop across N. What are the potential drops across M, P, and Q? Okay, so firstly, we can start off by thinking that because this is a 20-volt price and then this is like a circuit that's connected in parallel with this, I guess, suppose. Well, this is 20 volts basically, and this will also be 20 volts across P and Q and across L and M. Okay, so if this is a 7-volt drop, then in M you must have a 20 minus 7, which is a 13-volt drop. Okay, so this is a 13-volt drop. Then if I look at this circuit of L, N, and P, which is going like this, then I have to see that because this is 7 and 4, right? So in P, I'm going to have a 7 plus 4, which is going to be an 11-volt drop, okay? Like that. So till now, I have for M 13 and for P 11. So I've already got the answer basically. It's C. But then let's verify that Q is 9. So obviously, because this is 11 in P, and I told you that P's drop and Q's drop together will make 20 volts. So then you must have it as 20 minus 11. 20 minus 11 is actually 9 volts drop. So that verifies that. Yeah. And let's just carry out another verification of this. So we'll also verify it in this way that, like, again, we're going in that direction for the loop. So then you have 13, and then you have so yeah, minus 9. And I'm not really sure if I'm doing this right, but like, point is like this is definitely right because that is the answer. I guess there something have to do with the arrows maybe, because this is a dividing point. Is it going like that or what? So then you would have 13 minus 9 minus 4. That's going to give you 0, I suppose. But the point nevertheless is that the answer is 9 volts. And again, you guys are free to correct me in the comments. And next we have the question 36. A potential divider circuit consists of a cell of negligible internal resistance in series with two variable resistors of resistances R1 and R2. The potential difference PD across the cell is V0. The PD at the output is V. So which statement is correct? The potential divider, and the potential divider basically just splits the potential difference from the source into two parts, right? And across the components, I mean. So then which statement is correct? When R1 increases, it takes a greater proportion of V0, so V decreases. So if R1 increases, then it does take definitely a greater proportion of this V0, because basically the potential divider, like, it's all about ratios, really. If you're good with ratios, then you should be fine with potential dividers, really. So V out over V total equals R out over R total. And in general, or in other words, I suppose V out, taking R1, R2, and V out is equals to, for example, if I'm taking the potential difference across R2, then that would be R2 over R1 plus R2. So R out, I'm assuming it to be R2. If you want it for R1, then you would take R1 over R1 plus R2, and then you multiply this by simply V total, right? Similarly, here you have so V out for 2, then you have V out for 1, into V total. So it's all a ratio game, really. Okay, now anyways, when R1 increases, it takes a greater proportion of V0, so V decreases. That is correct. It takes a greater proportion of this V0, and so I don't know, Vx or whatever it is, I'll just call it, that increases, and so this V decreases. So that's correct. I'm going to say A is the correct answer, but let's check the other options anyways. When R1 increases, the current, let me just erase this for a while so that I can see the other options. When R1 increases, so it's increasing, the current through R1 and R2 decreases, so V increases. I think one of the assumptions for a potential divider is that because V is changing, R is changing, so you assume that I is pretty constant. I think I mean I don't remember perfectly, but I think so. So yeah, so I would probably cancel that out because the current through R1 and R2 increases. I don't think that's likely to happen because I mean, how can you have all three of them changing? I mean, that's kind of too much. When R2 decreases, I mean, you could, but like, it's annoying to consider that. When R2 decreases, it takes a smaller proportion of V naught, so V increases. When R2 decreases, it takes a smaller proportion of V naught, that is correct, so V increases. No, if it takes a smaller proportion of V naught, then V should decrease because there's direct proportion, right? So that should be wrong. And then when R2 increases, the current through R1 and R2 decreases, so V decreases. Now again, I don't really like the fact that current is changing, so I'm just going to cancel that, and so A is going to be my correct answer. Okay, next question. Question number 37. A nucleus of uranium 238 23892U decays in a series of steps to form a nucleus of lead 206 20682 Pb as shown. An alpha particle or a beta particle is emitted during each step. What is the total number of beta minus particles that are emitted? So it's beta minus. So an alpha particle is basically 4 to alpha. A beta minus particle is basically 0 minus 1 beta minus. Yeah. So then that means that obviously beta minus particle will not change my nucleon number. It will only change my atomic number, right? Or in other words, you can call it a nucleon number, you could also call it a mass number, and the bottom one you could call it an atomic number or a proton number. But anyways, my point is that that will not change the top one. So then if 4 to alpha, so I can check, so 238 minus 206, right? So that is 2 3, so that's 32. So if I have a change of 32 in the nucleon number. So then, because obviously a beta minus particle will not affect the nucleon number, but the 4 to alpha will, what I can do is I can take this 32 and divide it by 4. So 32 divided by 4, that is going to be 8. Okay, so basically I have 8 alpha particles emitted, and I know that now as a fact. Just take a different color. Okay, so that happened. So I have 4 to alpha times 8, which means well, I already know that that changed by 32. But then what about the bottom one? 8 2s are 16. So that changed by 16. So if I have 92 uranium originally, I have to subtract 16 from that because of all the 16 alpha particles. So then 92 minus 16, that's going to be 76 now. Okay, so I would have expected if there were only alpha particles emitted that this would be 282 76 PV, but that's not the case, is it? So then that means obviously, as they mentioned, that there's also beta minus particles being emitted, and therefore how many beta minus particles are there being emitted? Because it's 0 minus 1 beta, right? That means that my if those are emitted, then I would have my proton number increasing. So from 76 it would increase. So I will find the difference now, 82 minus 76, to find out how many beta particles are emitted. So 82 minus 76 would be, you can tell the mental math is not very good. I have to practice more. But anyways, it is 6, right? So that means I have 6 of 0 minus 1 beta minus. You understand my point? Because beta minus will increase if beta minus particles are emitted, then you'll increase this one, the proton number, okay? Because it's minus 1. And this was 8, okay? Could write it like that. And so another check you could do here is, now I have this equation like this. So you could say 206 plus 32 is going to be 238, and then 82 plus 16 minus 6 is going to be 92. Yeah. 82, 10, yeah, that's 92. That's a check you could do to check if your answer is correct, to check if both sides have balanced nucleon numbers and proton numbers. Okay. And therefore, Yeah, I got the answer as 6. So what is the total number of beta particles that are beta minus particles that are emitted? That's 6. Okay. Now let's go to the next question. Question 38. So which statement about alpha particles is correct? Alpha particles emitted from a single radioactive isotope have a continuous distribution of energies. Yeah, that is not really true, because I think all alpha particles, would have the same initial kinetic energy, whereas beta particles, yeah, they have a wide range of kinetic energies, because when a beta particle is emitted, there's also the emission of electron antineutrinos or electron neutrinos. So then beta particles would have a wide range of kinetic energies, whereas alpha particles, they have the same initial kinetic energy. Then alpha particles have less ionizing power than beta particles. No, that's wrong, because actually alpha particles have the greatest ionizing power, then comes beta, which has a medium ionizing power, and then gamma has a very low ionizing power, right? The charge of an alpha particle is 1.60 plus 1.60 into 10 power minus 19 coulombs. The alpha particle is a positive one, that's true, but then it's 4 2 alpha. Um, so then it has 2 protons, it's plus, and it's 2 plus. So that it has a charge of +2 actually. So it should be 2 times that, I think, yeah. And so that's wrong, and so D must be the answer, but if you just check it, the speeds of alpha particles can be as high as 1.5 into 10 power 7 meters per second. So to my knowledge, alpha particles are very slow comparatively compared to beta, which has like 10 to the power of 8 meters per second speed. Gamma has the speed of light basically, which is because it's an electromagnetic wave, so it has speed of 3 to 10 power of 8 meters per second. But then alpha is around the magnitude of 10 to the power of 6. But then again, I suppose that's an average or something. But then 10 to the power of 7, 1.5 into 10 to the power of 7 is also possible, I suppose, depending on the isotope. Maybe, I don't know if I'm saying everything right. So yeah, but I do believe that D is the most correct option. All right, then we have the next question. Yeah. So question 39. The nuclear equation shown has a term missing. So what is represented with the missing term? Well, if you see, the nuclear numbers are adding up, so 14 on this side and 14 on that side. Here we have 6 on the left, and then on the right we have 7 minus 1, which is also 6. So there's a term there which has no mass number and no proton number, so it's basically um a very very light particle which has no rest mass and no charge, and so it's not an electron or a positron. We anyways have an electron here already, and a positron would be 0 plus 1 beta, right, which is beta plus decay. But then it's either an antineutrino or a neutrino, and then we know that because this is 0 minus 1 beta, which means it's beta minus. Yeah, so with beta minus decay, you actually get an electron antineutrino, right? So it's like that. You get an electron antineutrino with beta minus decay, whereas with beta plus decay, which would be this, you would get an electron neutrino. Okay, so then that means that the answer is going to be, because it's beta minus decay over here that's being shown, so it's going to be an antineutrino. Okay, so A is going to be the correct answer. Then we have finally the last question. So which particle is a fundamental particle? So we have electron, hadron, neutron, and lepton. So the families of particles, like there are, I guess, two main families, at least that I know of, which are hadrons and leptons. So leptons literally means light in mass, whereas hadrons means bulky or heavy in mass. And so leptons are all the particles that are fundamental and are not affected by the strong nuclear forces, whereas hadrons, they can be divided into quarks. So they're not fundamental basically. And then, obviously hadrons are then going to be protons and neutrons. At least those are the ones that we need to be concerned about, I suppose. I don't know much. I mean, how much more there is in particle physics, but then in leptons you would have the fundamental particles, which are basically the electrons and the positrons, and neutrinos and antineutrinos. Sorry, that's not antineutrino, is it? Sorry, I reversed. This is the neutrino, and this is the antineutrino. But you get the point. These particles cannot be divided further, whereas protons and neutrons can be divided into quarks, whereas electrons, positrons, neutrinos, antineutrinos, they cannot be divided further, at least I think until today's research. But then I don't know, I've not been following research, so maybe they can be divided. I don't really know, but that is what I know for now. So then, if which particles are fundamental particles? Hadrons are by definition not fundamental particles because they can be divided into quarks. And then neutrons and protons are hadrons, so they are not fundamental particles. Electrons, they're leptons, and thus they are fundamental. And so the answer is going to be A. And we are done with this paper. It was quite fun, although I'm not really sure. I'm not really as confident with my physics knowledge as with my chemistry knowledge, so I don't know. I might have made mistakes, so if I have made any mistakes, kindly tell me in the comments, and have a nice day.